Хорошо, скажем, это Okay. the video from this type of thing that is shown. And the post.
Okay.
I'd like to welcome our colleagues from Kazakhstan. And our colleagues from city Farabi. But there is some changes in program. Today, instead of that we will talk Jammu will talk tomorrow. Instead of
Yeah, okay. Thank you Anna, for opening. And I'm happy to announce the first speaker of today, Pavel Exner from Prague, and he will speak about special properties of quantum lattices. Please.
And thank the organizers. I believe that as the first speaker, I can do it. All the speakers enjoy being here. Okay, my title is here, and it concerns quantum graphs, and I spoke extensively about quantum graphs last year at the summer school. So I believe that many of you were here. So there was no need to repeat the long introduction. And in a case, I have half an hour only. So just briefly. So quantum graphs were discovered by Linus Pauling about a century ago, rediscovered in the 80s, and since then are heavily flourishing. You can put on graphs various equations, Schrödinger, Dirac, which is of interest in condensed matter physics, but you can put there other equations, nonlinear, elasticity, wave equation, whatever study quantum chaos. Just I will mention some monographs where you can learn more. The first three were here last year. Since then, a big book by Pavel Kurasov appeared, which I also can recommend as an interesting reading. Now, The topic of this talk concerns the vertex coupling. So I have a metric graph, and the important thing is how I match the wave function at the nodes of the graph. And there are many ways of doing that. In fact, the most general form of the conditions is like that. Actually, since my equation is of the second order, it's Laplacian. Then the boundary condition involves the values and the derivatives, and the most general form of the conditions is just such a linear relation. And in order to make a Laplacian on a metric graph self-adjoint, you have to require two things. First of all, if you arrange the coefficients, matrix coefficient A and B to n by 2n matrix, it has to have a maximum rank. And second, this combination must be Hermitian. Now, this is usually ascribed to Kostrikin and Schrader, but as Barry Simon used to say, in Soviet Union, they knew everything one generation earlier, so you can find the same condition already in Roffe Beckett of 30 years before. Now, this is, of course, this form is non-unique. You can find different ways how to make it unique. One which we will use is the one below. That is A and B are chosen like that, where U is n by A and unitary matrix. There are many examples, and the one I focus on would concern the extensions or the operators which violate the time reversal invariance. And the simplest, the canonical example is here. I choose the matrix U in such a form. The first side diagonal and here in the corner one. Actually, you see that because the S matrix is the matrix U is nothing more than the S matrix at the momentum 1 or 1 over L. Then you see that a particle coming on the first edge leaves on the second edge from the second to the third. So obviously this is time reversal non-invariant. Now, this was introduced in this paper we wrote, is Miloš, and it has various interesting consequences. Of course, if you take a star graph with this coupling, so the essential spectrum is not affected, just the positive real line. But there is always a negative spectrum if you have at least 3 edges connected. And the S matrix is given by this formula, which looks like something which at the limit where K goes to infinity goes to the unit matrix, to trivial scattering. But it is formal, and it is true only if the spectrum of the matrix U does not contain -1. And this has a consequence for the scattering on such a graph. That is, if the vertex has an odd degree, 3, 5, etc., then the scattering at high energies is trivial. The edges are effectively decoupled, while for even degree of the vertex, the scattering is non-trivial high energies. Last year, I illustrated it on various examples. For example, the example of matrices, lattices which are square form and hexagonal form, and show that the spectrum is completely different. If you have square lattice, then the spectrum of a periodic lattice is, of course, composed of bands, but the bands dominate the spectrum. On the hexagonal lattice, on the other hand, it's the gaps which dominate the spectrum. Now, before coming to further thing, let me mention 2 examples of such couplings, more general, because I will need them in the following. Both are what I mentioned briefly last year. That is, the first is about PD symmetry. Now, PD symmetry any symmetry on a graph when you consider Laplacian concerns what happens in the vertices, because Laplacian on the edge, there is nothing what you can do with. If you want a symmetry given by some theta, then the coupling matrix U must satisfy this relation. So in particular, if you speak about time reversal invariance, which in this case is just complex, time reversal is the complex conjugation. So in order to have the matching condition invariant with respect to time reversal, you need that the matrix U is invariant with respect to transposal. And if you want something which is PT symmetric, then of course the parity operation must act the same way, because if you apply it twice, you have to return to the original state. So the question is how you choose the operator theta p, which represents the mirror transformation. For simplicity, I will assume that my graph is planar. Now, if the graph should be PT symmetric, it must act as the transpose again. Now, one way how to find the matrix is to realize that you can always diagonalize a unitary matrix, and a diagonal matrix is invariant with respect to transpose. And in addition, you know how the matrix which diagonalizes a unitary matrix looks like. You simply take the eigenvectors and arrange them into a matrix as columns. So if you do that, you will find that the matrix is in the form V transpose V, where V is the diagonalizing matrix. Now, if you do that, you will find that the entries of the matrix theta representing mirror transformation are like that. Note the complex conjugation. Was it without, it would be trivial. And for a general U, of course, it cannot be interpreted like that. But there is a class of matrices for which it works. And these are circulant matrices. That is a matrices which has all the entries on a particle diagonal the same. So these matrices have interesting properties. You can relate the values of the diagonals with the eigenvalues of such a matrix. And what is important, every such matrix has the same system of eigenvectors. They're simply given. They're given here. They're just in terms of these complex roots of unity. And since you know that, so you know how to diagonalize. The diagonalization of such a matrix is given by a discrete Fourier transformations. So if you use this V, you'll find that the matrix is like that, and that's like a mirror transformation, because the upper left corner, one edge is left, and then these ones are on the first side anti-diagonal. So these two are swapped. So you looked on your graph in a mirror. Now, two examples of such a coupling which go beyond this simple one. One, if you take U and now you rotate the U, you multiply it by a complex number, and then of course the matrix is still unitary. But if the former matrix is -1 in the spectrum, if you rotate it, it disappears, unless of course you turn it enough so you get another route to the position of -1. Okay, so now let's consider the example when you have square lattice, periodic square lattice, and each node you have this condition with this matrix epsilon R. You get the scattering matrix, which is like that, and it is once epsilon is non-zero, once you rotate the matrix, the limit of the S matrix is trivial. So there is an effective decoupling at large energies. And now how the spectrum looks like. So you proceed in the standard way. That is, you write an ansatz on each edge. It's a combination of exponents, put it into the boundary condition, the block conditions, and you get the system of linear equations for the coefficients. So the ansatz is here. And in order to solve the corresponding system of linear equations, you have to look where the determinant of the system, which is written here, vanishes. Now, the conditions, if you evaluate the determinant, the conditions are now like that. Was it the original lattice with the R coupling? Then only C1 and C3 survive. The last two lines. And then, of course, such a lattice has a number of flat bands, because these terms contain sine KL. So if this is 0, at these values of the energy, you have an eigenvalue which is independent of the block of the quasi-momentum. If epsilon is different from 1, then these flat bands disappear, with one exception. Namely, there is a particle value of mu for each value of epsilon for which there is a flat band. You can simply find it if you look at this condition. So if you annulate, if you take k equal 1, so the condition is simply the sum of the coefficient from 0 to 4 is 0. And if you look at this condition, you get the relation between mu, between the exponent of the complex factor, and the value of and the value where the flat band appears. Now let me show you some pictures. Maybe the point is that if I said that in the square lattice, the spectrum is dominated by bands. There are gaps, but they are asymptotically the relation of the bandwidth or the gap width to bandwidth goes to 0 as the energy goes to infinity. But if you rotate the coupling, then you get you are in the situation where the band gaps should be dominating, and the gaps roughly they should behave like that with mu, with the power of the complex factor. But this is only approximate, because then, of course, if you proceed with the complex, you get the situation where the -1 is again an eigenvalue. What is clear that whenever epsilon is not a multiple of pi half here, then the spectrum is dominated by gaps, which means that this number here, which is a probability, if you randomly choose a positive number, is in the spectrum, is 0. That's the quantity introduced by Band and Berkolaiko, and it will appear in a more interesting connection in a while. Now, the spectrum has again always a negative component. And the bands which are there, they will shrink to star graph eigenvalues as the energy goes to infinity. Here is the picture of the spectrum. So the positive spectrum as a function of mu, the complex factor was E2 I mu. So as mu changes from 0 to pi half, you see that the spectrum goes down. You also see that the value of 1 at particle value of mu, there is a flat band. That's the dot here or dot here. And if you look at the band spectrum as a function of mu, you see what I said. That is in In the case where you have the original coupling with, which does not decouple at high energies, you have mostly bands in the spectrum. And then the bands then start shrinking. But when you return and you turn one quarter of the full angle by half, then you restore the original situation and it's the same spectrum as before. One funny example, you can have gaps which are closing for particle values, and you see one example here where you have nice Dirac cones in this situation. But okay, that was one example. The other example is that you can consider interpolation between this coupling and the delta coupling, which is the most common one. I mean, that the function is continuous and the sum of the derivative is proportional to the common value. So you can try to find the interpolation between the two and look what it means. Which means that you want to have a family of family. Is there a water here somewhere? No. Well.
Okay.
Okay. So you have a family of unitary matrices dependent on a parameter which goes from 0 to 1, and is the matrix corresponding to delta for 0 and the R matrix for 1. Now you can choose it in different ways. For example, you take the eigenvalues which behave like that, and you construct the corresponding matrix U. Now, this can be tested on various examples. One is, again, take a square lattice, and then you look how the spectrum behaves as the interpolation parameter changes. I will not go into details. I will just show you two pictures. One is when you interpolate between the Kirchhoff coupling, that is the simplest one, continuity plus 0 sum of the derivatives, that's to the left. And you see that on the left for Kirchhoff's, the spectrum is a positive real line. There is always a negative band and there is nothing for Kirchhoff. And here it's why so, because a negative band escapes to minus infinity if you go with the interpolation parameter to 0. And the second one is with a delta with a negative coupling constant. Therefore t equals 0. There is a negative spectrum, but two bands, and the second one escapes to 0. Okay, there is another example which I will not describe. That is a loop chain which we studied first for this error coupling. But you can find interesting things when you, instead of this coupling, you take again the interpolation. But I will not go into that because you will hear this this afternoon from Honza Pekash, or you can read it in this paper, which is due to appear in Journal of Mathematical Physics. Now, let me now return to the original R coupling and show you two more examples. Which I have not mentioned last year. Okay, so one is the Kagome lattice. Kagome lattice is like that. It's periodic and the elementary cell contains 3 points. And here you have a parameter which is of interest. Namely, you can change the ratio of, I hate this thing, but I will use it, yeah. So this is this thing here, ratio of this thing and this thing. And the spectrum, of course, depends on how this ratio looks like. If you take the picture of the band spectrum, it is like that. And now I will ask, if you choose a particle value of this ratio, and take a vertical line and compute the measure of the spectrum, that the probability that the random chosen number is in the spectrum, you might believe that, I mean, it depends on the ratio. But this is not the case. Actually, this is a universal value as long as the ratio is irrational. Namely, for all irrational values of this ratio, you get this number is something like that. Actually, I mean, that's a numerical value. You can write down analytic expression, but it's clumsy, so I will not show it. But it comes from this thing. The spectral condition looks like that. And actually, the points in the torus, where the spectrum is this shaded region. And Band and Berkolay observed then in graphs, if you have edges which are not commensurate, this number is universal. Why so? Because the spectral condition, it goes through the torus. And if you have incommensurate rate, the slope of the sink is irrational. So then your trajectory from 0 to infinity covers this torus ergodically. And then, of course, the probability is just the area of the shaded region divided by the area of the square. And just to see that why the irrationality is important, we can do the same, but now we take rational values of the ratio. And here it is. If they are the same, it's the ratio of 1/2. You see, it's wide of mark, 1/3, 2/3. And if your rational approximation approaches irrational values, it goes closer and closer to this universal value. So that was one example. Another example, Cairo lattice. That's less common. That's a lattice which combines vertices of degree 4 and 3, which is interesting because at high energies, 3 is effectively decoupled, 4 is not. So you can again find the spectrum. It has absolutely continuous bands, at most 3 bands in the negative part. And what I will do, I will now add this scale fixing parameters in the condition in general different, and the vertices of degree 3 and degree 4. So if they are both non-zero, then of course the gaps dominate the spectrum because there are vertices of degree 3. So there are no paths where you can go infinitely long within the graph without meeting at the vertex of degree 3. But you can make it transparent, and moreover, you can do it in 2 different ways. First of all, in vertices degree 3, you can take the scale parameter to 0. In the limit, you get the Kirchhoff condition, which of course is transparent. And the second way is that at the vertice degree 3, you replace the matrix R by -R, which means that the eigenvalue -1 disappears. And again, you have transparency. And what you find is that in both cases, again, the probability of finding a value in the spectrum is non-trivial, and it's given by this number, again, numerically, but it's the same number, which is strange because, I mean, there's 2 completely different things. And why it's so? Okay, so here are the pictures. Again, the same thing. You have a torus, you have the condition, and you have 2 different pictures. But if you look closely, you see that if you shift, say, the right one, pi½ up and pi½ to the left, you get the same picture. So, I mean, analytically, they are the same. Okay, the next thing is now I take again my lattice, square lattice with the R coupling, the simplest example. But what I will do now, I will put it into homogeneous magnetic field. And why so? Because magnetic field naturally violates the time reversal invariance. and the coupling I have does the same. So we have two mechanisms, and we are interesting how these two mechanisms compete or collaborate. So what you do is that you again, first of all, you have to choose something which is manageable. So we choose the flux, which is rational. I mean, flux through the elementary cell of the graph is rational. And then depending, flux is P over Q, depend how large is Q, because then you treat it as a periodic system with a larger cell with a unit flux, because unit flux is something which you can gauge away. So if you have given Q, then the problem reduces to the system 4Q linear equations. So we went to 12, 48 linear equations were just enough. So here is the condition for Q equal 2. You get such a condition which gives bends given by the inequalities below. And if you numerically, so you get such a thing here. Fine. So the K is the momentum, the square root of energy. In the negative part, you have square root of minus energy. If you now take 1/3 and 2/3, Q is 3. So you get again the condition which I do not write, and you get two such. And you proceed up to 12, where we stopped. And what you get is this thing here. Now, you see that there is something which in the right part of this, it reminds you very much of the Hofstadter butterfly. In the left part, for small values of energy, it's something like a butterfly, but seriously distorted, which tells you that the violation coming from the vertex conditions is dominant, or it's vital at small energies. And if you go with the energy up, it's the magnetic field which takes over. Now, why so? Let's look how the time reversal invariance is important depending on the energy. I said that the time reversal invariance is a violation of the transposal symmetry. So the natural measure is to take the S matrix and the transpose S matrix. You take the difference and ask for the norm. So you can evaluate the S matrix, and you know now for this the S matrix, the M is the difference of the S matrices, and it's something, and the fact which is the object which is in curly brackets as an eigenvalue which is circulant matrix. So you can write down the eigenvalues like that, and from the eigenvalues you can estimate the norm. And well, I mean, time is running fast, so I will just skip the thing. I'll tell you just, if you look at that, you'll find that the quantity which measures the violation goes to 0 as the energy goes to infinity. So at high energies, the time reversal violence coming from the vertex coupling is negligible. And I explained the fact that that's only the magnetic field which plays the role there. Okay, here you can just, for example, in the simplest cases where the vertex degree is 3 and 4, you have explicit expression, and you see that they are like that. Even if you go with the energy to 0, again, the violation disappears, and it disappears at a high energy as 1 over momentum. Okay. Now back to the picture. So the dominating part is the Hofstadter butterfly, and if you in addition to the butterfly, you have also other parts which are there and which come from the coupling. They are here. You see that between each butterfly there are two strips which are the remnant of the vertex coupling, and they are energetically of the constant, asymptotically constant widths, and they do not disappear. But you may ask what the measure of the spectrum is. You would expect, if it's butterflies, that if the flux is irrational, then you're back to the 10 Martini situation. That is, the spectrum would be a Cantor set of Lebesgue measure 0. So we cannot do that. We can only conjecture. But what we can do is to calculate the spectral measure for rational values. And here it is, depending on the flux, between 1 and 0 quantum. And it's interesting to compare because for the original Hofstadter butterfly for almost Mathieu equation, there is a conjecture by David Tholes about the measure of the spectrum in the rational case. It is here. So explicitly, it goes to 0, and it's like 1 over q, and the constant is explicit in terms of the Catalan constant. And now we compare the two. And you see that our values of this the spectral measure are very similar to those of the Tholes conjecture. Now I've lost 3 minutes or something like that. Do I? Okay. One thing which is new, and I would like to the manifestation in finite graphs. So last year I showed you a comparison of the platonic solids, and I showed that the spectrum of the four of them is trivial at high energies, decomposed edges, but for octahedron, which has vertices of degree 3 of extra series. And now let's look like what happened if you now deform this thing. You take topologically same graph, but with different edge lengths, and I suppose that they are irrationally related, incommensurate. So then I cannot compute the eigenvalues analytically, but I can do it numerically and look at the spectral distribution. So here is, for example, if you look at the cube, and you see that it's something like 80,000 eigenvalues, and I plot this distribution of the distances between eigenvalues, of the spacing, and you see that the distribution is pure Poissonian. It's simply a family of independent edges. And now, when I take say an octahedron and deform it, I see you have this thing here. So it fits perfectly to Gaussian orthogonal distribution. And that's interesting because there is a paradigm in the literature which say that if you have a graph with incommensurate edges, then if the graph violates the time reversal invariance, you have Gaussian unitary ensemble. This one violates, but you have orthogonal example. And the reason is, again, the high energies, the violation is disappearing. And finally, the last, Kirsten, don't fly again. If you take now the same graph, but instead of the rotating thing, I rotate the matrix U very little, say 100ths. And instead of this graph, what I will do, again, a Poisson. So indeed, the properties of the vertex coupling are showed in that region. So it comes from the work in preparation. And I think, thank you for your attention.
Thank you, Pavel, for your very interesting talk. We have not so much time for questions. Actually, we have -1 minute.
I am at disposal to everybody.
But maybe there is, but we can accept one question on the part. Okay,
Alles
I
klar.
have a question, but I don't have it. So let us next speaker. So we continue immediately. Next speaker is Henrik Winkler from my university, if you don't mind. And he will give a talk. He will give a talk on harmonic systems of the differential equations on starlight graphs. Please tell me.
So, thanks very much for inviting me, and many thanks to the organizers of this nice conference. So, today I want to present a topic about Fourier transformation and spectral theory for canonical systems, which are on a star-like graph. So, a star-like graph, yeah. Such a thing, which is connected at one point in the middle. And at this point, you have certain interface conditions. The aim is to get a self-adjoint operator on this star-like graph and to make some spectral theory and to describe there some spectral properties. It's a joint work with my friend Henk de Snoo from the University of Groningen. At first, I have to introduce what a canonical system of differential equation is, and appropriate to this problem here. Let's say here we have the 0 at this point. It's convenient to consider canonical systems on the half-line. Mark Grigorievich Crane really did much of this theory. And I have to mention Louis de Branche, who in a different connection concerning certain integral systems also considered canonical systems. And with his techniques about Hilbert spaces of entire functions, he finally was able to prove an inverse spectral theorem for these canonical systems on the half-line. I'll come later to the story, but it will be a little bit short. So what's going on here? We have here a system, jy prime is minus c. This is a spectral parameter. H, that's a deciding thing here. That's a Hamiltonian, depending on x, yeah. It's a non-negative matrix, as you see. And then you have this yx. And this J, this is such a direct matrix. Ij is a signature matrix. Is it now better, or can you listen me? Yes. Which is here important. Once a physicist told me that this J is coming from Newton's old principle of actio is equal to reactio. Maybe that's what's behind the whole story. This is also typical for this classical canonical Hamiltonian systems in physics. Yeah. So the Hamiltonian non-negative definite has then 3 components, H1, H2, H3. And okay, all of them shall be locally integrable. Now, a boundary condition belongs to it. So y is a 2-dimensional function, yes. So the first component of y at 0 shall be 0. This corresponds, if one reformulates this as a Laplace equation, if H is equal to the unit matrix, to a Dirichlet condition. And now, yes, it requires some many calculations to show if the trace of this H is equal to 1, so one can consider trace normed Hamiltonians. Each Hamiltonian can be trace normed. Apart, we want to avoid the Hamiltonians which are equal to 0, yeah, because this gives no, on some interval, this gives no contribution. And if this is the case, actually, if the integral over the trace is infinity, that's a more general condition, then we have Weier's limit point at infinity, Weier's limit point case. Yeah, this means you have then a unique Titchmarsh-Weil coefficient. And well, if you look at this, maybe I can go back here. If you look at this equation above, it turns out that J has, to satisfy this equation, J has to satisfy a simple property, namely, there might be intervals where H is of rank 1 and constant. If it's trace normed, then it is of this form as you see here, yeah, with the cosine phi and the sine phi. So phi is not x dependent here, yeah, it's really constant on such an interval. And if you multiply the former equation by cosine phi and sine phi, then you see that if H is of this form, then it vanishes. So this means the derivative of the J is 0 on such intervals, yeah. And one has to put this into consideration if one wants to construct a corresponding Hilbert space. Where this equation is living. And with this, one can define the corresponding Hilbert space. That's the usual standard inner product here given by this Hamiltonian H, with the additional condition that this on this H indivisible intervals of type phi, we call it then, yeah, then cosine phi sine phi times f is constant. Well, one can say almost everywhere, but this doesn't matter here much. Now we come to the spectral theory. To this end, we have to introduce n-dimensional so-called never-linear functions, yeah? Sometimes we can also call them spectral matrices also, but there's a different notation. So what is it? It's a matrix function which all the components are analytic, yeah? Mapping the upper and the lower half plane to the complex plane. And it has this property, well, that omega of these omega z bar star, yes, this is the transpose, and that's this kernel omega z minus omega mu bar divided by z minus mu bar is also non-negative definite, yeah, for all z and mu. And it turns out that this has an integral representation, yeah. There show up some matrices. Here you have a matrix B, which is non-negative definite, A, which is self-adjoint, and then you have such a spectral measure sigma. It's such an n-dimensional non-negative definite measure, such that this integral here below is less than infinity. So that's the classical representation theory for this never-linear functions. And of course, let's go back to the systems. How is it if we have such a canonical system given, then we can introduce a fundamental matrix. Here, I must say, please don't be astonished. It looks a bit strange, but Mark Grigorievich-Grain did this all the time to introduce a fundamental matrix in that way. Nowadays, let's say, so the fundamental matrix is a transpose of this W. So please don't be afraid of this. But we kept this because we had some references to the papers of Mark Wein all the time. So I'm sorry for doing this. It's for historical reasons. And Now we can define the so-called Titchmarsh-Weil coefficient. It's a little bit not via boundary triplets, but adapted to this canonical system. It's a unique N1 function called Q, yeah? So it's a one-dimensional never-linear function. So that's this function chi, which consists of this W star, yeah? Here you see here, that's then the modern fundamental matrix, if you want to formulate it. So times this vector 1 minus Q of Z belongs to this Hilbert space, yeah? Actually, we have the limit point case, so there's only one of these guys which belongs to it. And now, a little bit short, the theorem of the branch, which is really a deep theorem. There is a unique correspondence, which is trace normed Hamiltonians, and this functions Q belonging to the never-linear class, yeah? So this is somehow an inverse and a direct spectral problem here, yeah? The problem is there were some, it was not really to find in the papers of Louis de Branche. If someone is familiar with his papers, yes, it's not always very understandable. He formulated this in a different way, but one could reformulate this with some efforts here, which also was then more or less a paper. And nowadays there are also some certain books, or one of them of Bemling, for instance, and some other books where this theory is explained in a more understandable way, let's say. So, and now we can get a self-adjoint relation. Now, this means it's now an L to H, so such a pair of functions belongs to this relation if this differential equation is satisfied with a boundary condition, yeah. And now we come back to Crane. This Titchmarsh-Weil coefficient, as I have shortly introduced him, this is equal to the so-called Q function corresponding to this operator A and also this chi, which was a solution in L to H, yeah? Shows a role. And this means that this kernel of the Q function has such a representation, yeah? It's such a resolvent representation, yeah? The kernel of this Q function, as we have it here, is equal to I, and then we have this inner product of I plus Z minus mu, and then times the resolvent of A. And now we come to the case of the canonical systems on our graphs. Now we consider here such systems. Let's say here we have H1, H2, H3, and here we have Hn. So we have now n Hamiltonians here, yeah? Which are connected by the zero. So we get now n of this canonical differential equations, of course. And we get a space L to fat H, which is equal to the direct sum of all these spaces connected to this n Hamiltonians, yeah? And now we have components which functions, each fi belongs to L to H, and we form then functions f by combining them, yeah? The funny thing is, what about the interface condition? And here we did it very explicit. So the interface conditions is by a pair of matrices here, P and G, and these are so-called never-linear matrix. So the advantage is that you really have here concrete matrices, which have to satisfy certain properties. Namely, P is an orthogonal projection, T is self-adjoint, they are commuting, and T acts as an identity at the range of I minus P, as you see here. So these are certain conditions you require to get a self-adjoint realization with this never-linear pairs, and then you get such a self-adjoint relation depending on P and T. And the interface condition, yeah, so we have Fg in this APT, we call it. It satisfies for each component the canonical system on the half-line. And the interface condition is now P, F2, 0, is equal to TF1. And as you see, if P is equal to the, if T is equal to the identity and P is equal to 0, then we get here the classical combination with a Dirichlet condition. This you see here, so we have here A0I, yes, this is just each, with each Hamiltonian here is connected such an operator, A1 till A2. And so on. And this L2H has a certain property, so it's equal to the domain of APT. And there might be also such a thing like a multi-valued part of this APT, yeah, which is usually not so pleasant, but it shows up. But the recipe to handle this is now Mark Rein's classical resolvent formula, as you see here, yeah. So APT is connected by our Dirichlet condition A0I, the resolvents, yeah, via that formula. And the Q is here the diagonal matrix, which is formed by all the Stitchmarsh-Weil coefficients corresponding to the corresponding, which correspond to the Hamiltonian. So we have here the 2 and so on. And here AN and UN. So this is the pairs you have. And now, okay, how to get now the Q function of this self-adjoint relation APT? One can calculate, we get it by this property. It has a representation of the form with some mu, which is not so important. And in the middle, you see this omega PT. And this omega PT is now a nice representation. It's very explicit, you see. It's just here the product of this I minus P times Q of C minus P multiplied by PQ plus T inverse, yeah? So we have here really an explicit spectral matrix now, yeah? Okay, this M is some more technical. But the funny thing is this omega PT belongs to a never-linear function, and a never-linear function has such a spectral representation, as you see. And this leads us to introduce a generalized Fourier transformation, which means each of this W transposed here, so that's the original fundamental matrix, we split into parts in V's and U's, yeah? Each of them are two vector functions. And then we form this diagonal matrices V and U. And then we take at first, that's the usual way, F with a compact then port, and then we can introduce via that inner product some functions F1 depending on F and Z and F2. And then we combine it with the P's and the T's, and we get the FPT. And now the funny thing is, going back to the resolvent, we can see that APT, so it's some, yes, required, so some page, 1 page of calculations, so yeah. The resolvent has now the representation with this FPT, so this means the FTP is the best candidate for Fourier transformation, times the spectral matrix, times this FTP again, yeah, so FTP adjoint times omega, plus some entire function which doesn't play any role. And if we consider E d lambda, the spectral family, so that's a classical theory, yeah, each self-adjoint operator has a spectral representation. Given by this via the resolvent, yeah, you have then as this integral over 1 over lambda minus z with this inner product here via this spectral family. And the spectral family has then a representation with this measure sigma, and the sigma shows up as a spectral measure of our spectral matrix omega pt. So that's again the never linear presentation of my omega pt. Yeah. And now we could show a theorem. So this FPT, as we introduced it before, the generalized Fourier transformation, turns out to be a partial isometry from L to H onto L to sigma, such that the kernel of this FTP is just the multivalued part of this APT. Yes, that's one detail one has to take into consideration, because APT can have a multivalued part. You cannot expect an isometry. But the operator part of APT, if you split it into the multivalued part and the operator part, yeah, is exactly the multiplication by lambda, so by the independent variable in this L2 d sigma, yeah. That's why we can call it, let's say, a Fourier transformation. Huh? And now we come a little bit noch, at least to the multivalued part and some results to isolated eigenvalues. Here it's a little bit technical. Yes, let's say we can only have a multivalued part. That's the basic idea. If our canonical systems, at least a few of them, start with such indivisible intervals of some type. So if 0, yeah, formulated in this way, is you just take the end of the, let's say, the maximal indivisible interval, yeah, which is constant, yeah. So we have here a kappa I, yeah, so kappa 1, kappa 2, and here we have so this of this type, CO5 by I, and so on, yeah. But not all of them might have such a thing. But we assume that the first one of them, the first M1 of them shall start with such an indivisible interval and the others not. So now the question is, what's the result? So we split this matrices so in M times N, yeah. And then we construct a matrix psi, again with this diagonal matrix. And this matrix psi is a good source of all things, which allows us really to calculate this multivalued part, because the dimension of the multivalued part of this APT is a dimension of the kernel of psi. So you only, now you have here a concrete matrix, yeah, consisting of these things. And if you calculate this kernel, you have the dimension of the multivalued part. And it's going even to be a little bit more explicit. So if we have X such an N times L, dimension rank of L of, as the rank of this X is a dimension of the kernel of psi, and with some certain technical conditions, yeah. This K is such a matrix which consists of the inverses of diagonal matrix, which consists of the inverses of this first, let's say, ends of the maximal indivisible interval starting at 0. And then this B equal to X times X is a linear term of my spectral matrix, yeah? This B which shows up in the never linear presentation. And you can explicit calculate it, this B is here equal to this imaginary part of the spectral matrix divided by such a limit. And so finally, some remarks to the multiplicity of isolated eigenvalues. Here you assume that you around point C0, yeah, in such a punctured neighborhood, my Q function is analytic. And there are two possibilities, either at that 0 you have a pole or you don't have a pole, yeah. Then it's analytic on complete U C0, yeah. So these are such circles around, let's say some circles around C0, yeah. So yeah, so if C0 is an isolated eigenvalue of the operator, then it belongs to the support of sigma I. And then we have a corresponding eigenfunction. And now we can define again here some functions fi. This is a little bit technical, yeah, you do it, it's very similar like here the construction of this function chi, which belongs to L2. So we have here two cases, either the zero belongs to the support or it doesn't belong to the support. And it has some properties, yeah. It's equals to this component U. And now we introduce still some more sizes. So we split now our 1n. So here we didn't assume that, let's say here we have here at first here at the first, let's say, else such poles and at the other places not. So we split this here into some Li, yeah, and to some Mi's, this large, yeah, and then we form again diagonal matrices. So if C0 is a pole, yeah, it belongs to this I1, and if it's not a pole, so there's just nothing, yeah. It's not the support of the spectrum, it belongs to I2. And then we have this different M, so we have two matrices now. We can also get this explicit. And then we have here, okay, some more technical property I skip. So some function C, this you can show belongs to the maximal operator, yeah, if it satisfies certain properties. And G satisfies this interface conditions if we have this property. And now let me come to the theorem. So we again assume that this Qi is holomorphic on this punctured neighborhood. So on C0, there's either a pole or no pole. And when is this C0 now an isolated eigenvalue of our operator APT connected with our Nevan-Linna pairs? Yeah, and this happens if this dimension of the kernel of this PM0 minus TL0 is bigger than 0, and then this M, and this dimension of this kernel here, you can calculate this in explicit way, is then the multiplicity of the eigenvalue, which is in a certain sense also a funny result. So, okay, good. And now I thanks for the attention.
Other questions or remarks? So the last formula, please go back one slide. So this is something like when you would use boundary retrieval, right? Then you can read off the pole order in the corresponding pole order of the Y function.
Yes,
When
yes.
you take the right
So one can also translate this in boundary conditions. Yeah. Then you are completely right. Yeah.
That's all. Yeah.
Algebraic or
I mean the geometric.
so it should be
Okay, further questions or remarks? Okay, then let's thank the speaker again and we continue with topic.
Okay, thank you.
Yeah, we continue. A little bit late already. People were so much news that the conversation is up to 11:49. Not very good. Okay. Let us continue with the next talk. Von Victor Global bounded solutions to the non-autonomous linear and quasi-linear first-order hyperbolic system, please.
Okay. Okay. This is joint result with Irina Kmit from Humboldt University, Berlin, and Institute of Applied Problem of Mechanics and Mathematics, Lviv, Ukraine. No, this is our last publication. We consider following system of quasi-linear hyperbolic equation in U n-dimensional vector in domain x from interval 0, 1 and t real time. F is vector function and A is diagonal matrix with separated elements for U in some neighborhood of identity, and xt from domain P. We supplement our system by boundary conditions too. Here are capital is so-called reflexive boundary conditions. And Hg is perturbation. This is a smooth function from two variables, and Qg are bounded operator from function from continuous function on interval 0, 1. No, for example, operator Q can be integral or delay, for example, here. Such equation has many applications. For example, one-dimensional Euler equation, Saint Venant system has application in mathematical biology, in laser dynamics, so on. No, for example, Saint Venant equation has following form. Here, H. So this equation describes dynamics of water in channel of length L. Here H is water depth and V is water velocity. And 5 is boundary conditions with, which are described by physical condition. We assume that all coefficients of our system are smooth and xt and v in some neighborhood delta. Assume that coefficients A are uniformly separated, and Qt for all fixed t, this is bounded operator from continuous space 0, 1, and family of operator has some smooth property. And perturbation function H are smooth also. Our main result is establish a condition for existence smooth bounded on the axis solution for our system, a small solution in some neighborhood of identity. If coefficients of system are almost periodic in T, we give conditions for that such solutions are almost periodic also. We rewrite system 1 in the form 7. We choose non-homogeneous part of right-hand side of system F small and the linear part B U. Our approach is usual. We construct sequence of iteration UK, formula 8. So UK plus 1 is solution of this linear non-homogeneous system. And boundary conditions A also linear and non-homogeneous. So we have two steps of our investigation. First, we need conditions for existence of smooth bounded on the axis solutions for linear system of form 8. And next, we prove that such sequence converges to limit function, which is solutions of our quasi-linear system. So first, we investigate linear non-homogeneous system 10 with reflexive conditions, boundary conditions 11. Assumption, elements of matrix A are separated one from another. All function in are smooth, so function A and B and F. First, we introduce generalized solutions of linear system. Let initial value is formula 13. If initial function phi is smooth with 0 values at the end, then it is known result that then such initial problem has smooth solution. So classical solution which has all derivatives. We introduce generalized L2 solution. So introduce approximate initial function phi by a sequence phi L from space C01. Then corresponding solution of such initial problem has a limit in space L2 for x and for all t at all bounded interval, for example, s plus s1. No, we prove that such solution exists. Now, if we consider homogeneous system, then for such solution, we can introduce evolution operator U capital. This, no, for all fixed T and S, this is bounded operator in space L2. And S function from T and S is satisfied no, usual conditions. So conditions of that this evolution operator upper formula and some continuous properties with respect to T and S. If an initial function phi has generalized derivative, so phi in space in Sobolev space H1 and satisfy boundary conditions, then these solutions have more smooth properties. So such solution is a continuous function with respect to t with values in space H1 and has derivative is if this function considered in space L2. So if we have such evolution equation, we consider our system in abstract space L2. So introduce operator A capital with domain U from Sobolev space with boundary condition. And non-homogeneous system has form 15 and initial value function phi. If function f small has some smooth property, for example, has first derivative with respect to t with values in space L2, then such equation has classical solution in abstract space. So is continuous derivative, has continuous derivative in space L2, belong to domain of operator A and satisfy equation. In our investigation, we assume that linear system has stability property. So we assume that every solution satisfies estimate 17. So stability is exponential stability with some positive constant k and alpha. In this case, equation has unique bounded on the axis solution with value in space L2 v star. This solution has uniform estimate in space L2 and for all t belong to space H1, but in space and satisfy boundary condition. But in space H1, this solution is not bounded on the axis. To obtain boundedness in space H1, we need some additional assumption on stability. So we assume that our linear system is stable in space L2 and also in space H1. Formula 20 for all initial function phi from space H1 and which satisfy the boundary condition. In this case, we have this solution V star is bounded in space H1 for all t, uniformly for all t on the axis, and using embedding theorem, we have that this solution is continuous with respect t in S and bounded in space C on 0, 1 on the uniformly on the axis. So we have continuous solution of our linear system, but for proving this result, we use usual approach integration along characteristic. So for coefficients AG, we consider ordinary differential equation 22. Solutions of this equation is characteristic of the system, and using this characteristic and separated of elements AG, we prove existence of our generalized solution. And using characteristic, we introduce several additional functions, CG, DG, and the operator G capital. This function will be needed for proving existence of bounding solution. So we have such result. We assume that coefficients are smooth of system. System is stable in space L2 and stable in space H1. We introduce several additional conditions, 26. In this case, we prove that our bounding solutions is smooth. For example, if coefficients are has one derivative that we have estimate 27 for first derivative, and with additional assumption about smoothness, we have we prove that these solutions has two derivatives and has such estimation. If all coefficients of system are almost periodic, then this bounding solution is almost periodic also. Here usual definition of Bohr almost periodic function. For proving, we have existence of continuous solution. For proving differentiability condition of these solutions, we use next representation using integration along characteristic. So our bounded solutions U star satisfy such integral equation. We write this equation in operator form. And using this representation, we prove smooth property of solutions. We can investigate this operator representation 29. For example, in such paper, we investigate this operator equation and give several conditions that operator identity minus C minus D is invertible. Of course, in such case, we have a solution of such equation and estimating from right-hand side the F small. If here we don't assume that linear system is stable. And of course, we prove, not of course, and additionally we prove if all coefficients of system are almost periodic, then this solution is almost periodic too. If all coefficients are periodic with some period omega, then unique bounded solution is omega periodic also. In a periodic case, we assume that evolution operator is stable in space L2. We don't assume in this case that evolution operator stable in space H1. It is enough space L2 and some additional condition, and we prove that this unique bounded on the axis solutions has such a smooth property and estimate by right-hand side. No, and estimate. Now, if we consider again our iteration, so we need we need condition such that all iteration of such form has bounding conditions of in our here also here all coefficients are periodic such that all iteration UK are periodic with smooth properties, and we need also uniform estimate for such solutions. So we for Baselinear system we consider small solution, and if UK are rather small, but we need also such that equation has solution also by small perturbation of all coefficients of matrix A and B. So these periodic solutions survive by a small perturbation. This is connect with surviveness of exponential stability of system by small of linear system by small perturbation of coefficients. So robustness of exponential stability by small perturbation of coefficients A and B. For perturbation of coefficients B, it is a well-known result. So system has bounded perturbation, and it can be proved that exponential stability survive. But most difficult part, small perturbation of coefficients by higher derivative coefficients of matrix A. In general, this problem is open. We can prove in generally such result. We have several we have several sufficient conditions. No, for example, in this paper, we consider system. We studied also quasi-linear system, but for linear system, we prove survivalness of not only exponential stability, but also exponential dichotomy but by additional assumption on boundary conditions. We considered so-called smoothing boundary conditions with some some degenerate boundary condition with some additional assumption. So for this system, for example, if system is autonomous, then evolution operator, in this case semi-group, has eventually differentiability properties. And similar here. In generally, we don't such result, but we have several conditions. For example, we use Lyapunov approach. For example, we introduce very simple Lyapunov function. Okay. Lyapunov function V, so a diagonal matrix V capital with some smooth properties, and some estimation as in Lyapunov theorem. Estimation for solution and some estimation for boundary conditions. In this case, the system is exponentially stable and has robust property. So all small perturbation of such system, of all small perturbation of coefficients A and B, this system also has exponential stability property. No, for example, this simple example, such non-autonomous system with usual Lyapunov function with diagonal matrix 1, 1 is exponentially stable. It is very easy to verify. No, so in now using result for linear system and for robustness of exponential stability for quasi-linear system, if coefficients are periodic with respect to t, no, we have following the result. So we assume that coefficients are smooth and t periodic in time. We assume several additional dissipative conditions and assume that system has robust exponential stability. Then in some neighborhood epsilon, in some epsilon neighborhood of identity, we prove that this system has unique t-periodic classical solution, and we obtain estimate for this classical solution. That's all.
Thank you for the talk. Are there questions or remarks? Yeah.
One question. What about parameter alpha in the theorem? How do you determine this parameter?
Which parameter?
Alpha in the theorem. How do you define this parameter?
In stability, alpha in.
Okay.
No, this is some positive constant.
Some.
Yes, and of course, later we obtain dependence of our epsilon delta from alpha also.
Depends on epsilon.
Yes.
Yeah, 1 second.
Thank you for interesting talk. First question is the matrix A, is it diagonal or it can be symmetric? Or
Is diagonal.
it's just diagonal.
Diagonal for x from one-dimensional space is usual
But
condition.
can you do for symmetric?
Not, we don't study such
Okay.
equation.
So the multiplicity is not allowed, right, on the diagonal? Multiplicity for metric as a diagonal, that it's not allowed.
No, this assumption for hyperbolic system.
Yeah, because like if it's everything is distinct, it's strictly hyperbolic. But if you
Yes, strictly.
it's strict, just strictly hyperbolic.
Strictly hyperbolic, yes.
Thank you.
This essential assumption, yes.
Okay, further questions or remarks?
About the boundary condition, local or maybe non-local form? Boundary conditions. Thank you. What about the boundary conditions? If the area is a local or maybe it's possible to institute with non-local forms? For example, without boundary conditions. Maybe some integral.
No, first part is rather usual condition. For example, in okay. No, for example, for Saint Venant equation, we have boundary conditions of form 5. So if B is constant, this is our reflexive boundary conditions. No, we consider non-perturbed boundary condition is non-autonomous. No. This is essential for us because we study using abstract approach. And H is some perturbation in our case. No, here in formulas 5, B can also such form. Using physical conditions for such system.
Some more questions or remarks? Then you can take the speaker again. Yeah, I start already. We're still a little behind. So next speaker is Evgenia Semenova, and she will speak about some different topic. The Boolean sum interpolation for multivariate function of bounded variation.
Dear colleague, I am pleased to present you my talk about a Boolean sum interpolation for multivariate function of bounded variation. And this research are conducted joint with Pristine in Institut Mathematic, University of Lübeck. And so we start with a short introduction to the topic. The interpolation of periodic function at equidistant nodes by trigonometrical polynomials is a basic task of approximation theory. And the most of current interpolation method make use of smooth functions, and the rate of this convergence take into account the smoothness of the function f and the corresponding error estimation for different type of smoothness you can find in the following monographs. Temlяков, Dung and Urlich. But in many practical situations, we don't know if our function differentiable or not. We only know its values in some nodes. And what's happened if our function has not enough smoothness or discontinuous? In this case, evidence we can focus only in the error in LP norm. And it turns out that the continuous is not necessary condition for convergence. It was stated by, it was stated by Motorny in 19 90 that that Riemann integrability of function is a necessary and sufficient condition for convergence of interpolation process if a number of our nodes tends to 0. And for a little bit more smoothness, the approximation order in LP norm can be bounded by the best one-side approximation. And this result would stay Preston Xu in 1994. And what now? Okay. And a particular important class of function, in general speaking, discontinuous function, it is a function of bounded variation. And the first result for function of bounded variation comes from Zacharias, and he proved that in L2 norm, the accuracy behaves like 1 over square root of n. And this result was generalized by Pristine in 1984 for any p bigger or equals 1. And this is my short introduction. And in my talk, we will focus on function of bounded variation. And let's state our problem. So let's our parameters p bigger or equals than 1, and we consider the space of function where we will measure our accuracy, and this is space LP over torus TD, and this is a space of integrable function with p power, and such spaces supply the following standard norm. To introduce our class of function, we need to decompose. Decompose our torus TD, and for each direction, we introduce the following set of nodes. And we will note by xi the corresponding vector, and you can see that each component belongs to the corresponding set of nodes zeta j. And also we will need the vector xi plus, and this is a successor to our vector xi. And the successor means that we take adjacent nodes to the corresponding component xi kj. Okay, the next. And now we introduce a difference operator, and for this we will make some additional notation. And D, this is a set of index, and B, also the set of index, is subset of our set D. And D difference operator is the following. So here by the double dot, we means the following vector. We means that vector consists of the components components from vector xi if j belongs to B, and otherwise we takes xi plus. So, and all possible combination of vector xi and xi plus we will sum, and it's make up our D difference operator. And the B difference operator is the same, but we have such sum over only over the B subset. And so the variation of the function on the torus TD, we introduce in the following way. We take our B difference operator and we take a supremum over all possible set of nodes zj. And the total variation of the function is the following. So we sum up all possible variation on function by the set of index B. And a function for which our quantity HV is finite, we will call a function of bounded variation on torus TD in the sense of Hardy-Krause. And now we are ready to introduce our interpolation process. And at first, we introduce the space of trigonometric polynomials. This is a standard form of the space. And at first, we need to introduce some grid. And we introduce a set of odd number of equidistant nodes in each direction also, in each direction J. So our set of equidistant grid has the following form. And if we take a tensor products of such grid, we will call such tensor product a full interpolation grid on the torus TD. And at first, we introduce our interpolation process for univariate bounded function, and it's look in the standard form. And here the Dirichlet kernel, 2n Dirichlet kernel. And also, I would like to pay attention that this index n means the power of 2, the power of 2. And also, we step by step, we introduce interpolation process for multivariate function on the one variable, and it will look like there. It's also some tensor product, and it will become the following process. And okay. And our interpolation process for index that belongs to the set of index B has the following form. So this is our interpolation process. And it is evident that our B, it can be equals D. D is a full set of index. And now there's also a short remark, the representation of our operator by its Fourier series. But it's Fourier series, so we have the following Fourier series, and this coefficient is C, K, B, we rewrite in the following form. And here X with 0, this is all possible combination of nodes in our grid. And so this is our results, what we obtain. For the function of bounded variation, we obtain the following order of the for the following accuracy. Oh no, following accuracy. Yes, this is for if P bigger than 1, and if P equals 1, we obtain a little bit worse accuracy because here we have some logarithmic factor. And it is interesting to know our corollary. So if we have the full set of index, so if B equals D, our accuracy will be the following. And if we have some isotropic process, so our set of equidistant nodes, set of equidistant nodes in H direction J equals, so we have the following order of the accuracy. We have the following order of the accuracy. And now we will introduce also interpolation process by on this sparse grid. And to make up this grid, we need a little bit another set of equidistant nodes. And we will introduce it in the following way. This is an even number of equidistant nodes. And for this set, for these grids, we need introduce another interpolation process. So it is interpolation process look like this. And here, k with 0, this is a 2 to the n power modified Dirichlet kernel. It's look like here. And it is very interesting that such interpolation operator creates the chain of interpolation operators. And this chain satisfies a very important condition for us, And due to this condition, we can consider a Boolean sum interpolation operator. This Boolean sum interpolation operator is look like the following. And here, big plus, this is a Boolean sum operation. And as you can see, here we have some tensor product of our interpolation process in each direction. And we have a Boolean sum over all such interpolation operator, but with condition our parameters R1, R2, RD, the sum of these parameters should be equals n. And such interpolation process has the following sparse grid on the nth node order, and these grids look like the following. This is I think it's clear. And the sum representation for such operator also it is known, and it was done by Bazensky in 1989. And I would like to present you our grids. So here you can find full grids for n equals 5. It includes 32 nodes, and here our sparse grid for n equals 5. And here you can see the full tensor product grid for n equals 6, and here the corresponding sparse grid for n equals 6. Yes. And what we have, our main results is the following. So if our function is bounded, have a total bounded variation, for the parameters p bigger than 1, we have the following order of accuracy. So, and it is very interesting to compare the order of accuracy for tensor product grid, for interpolation process in the tensor product grid, and interpolation process in the sparse grid. And here some comparison. So for accuracy for tensor product grids is the following. As you remember, 2 in the power minus n over p. And for sparse grid, the accuracy is by the order the same, but here we have some additional logarithmic factor, n in the power d minus 1. So for sparse interpolation process on the sparse grid, we have a little bit worse accuracy, but look at the nodes that we need for our interpolation process. For tensor product grid, we need 2 in the power dn nodes, and for sparse grid, we need only 2 in the power n with some logarithmic factor. So we have the sparse grid is much less than tensor product grid. So this is our main results and our perspective to the future. So we would like also to estimate a discrete Fourier coefficients. Also, we would like answer to the questions if f function of bounded variation, is it true for the R derivatives of the function f? And we also would like to have a similar results on the cube and sphere. So thank you for your attention.
Yeah, questions? Thank you for the talk. And questions? Let us thank the speaker again. Just to remind, there was due to ability of we made some changes in the program, and that's why the Cyberboy is now giving a talk, and John will give more talk. And then I don't know what you make this interface, but it's
Could you please show me my presentation?
Take one second. So maybe I can announce you, right? So the next talk is given by Cyberboy Mano, and it is about quantum dynamics of a particle in T-symmetric time-dependent shocks. Please.
Thank you. Thank you. Good afternoon, organizers, lecturers, and participants of this conference. First of all, I would like to thank the organizers for giving me this opportunity, that is participating and presenting our work in this wonderful event. The talk I'm going to present can be called quantum dynamics of a particle in PT-symmetric time-dependent box. Time dependence here implies moving boundaries or well-off trap. PT symmetry implies here the system is symmetric under the transformation of parity and time reversal. So the PT symmetric system can be introduced through either complex potential or by imposing proper boundary conditions. We treat such system in quantum mechanical level. The talk outlines as is shown here. After mentioning motivation, I will briefly introduce time-dependent box, then proceed to the case PT-symmetric quantum box, and then demonstrates obtained results that are observable quantities of such system. And finally, I will finish with a sketch for experimental realization and summary. The motivation for the study of PT-symmetric dynamical confinement comes from the fact that that allows understanding difference between static and dynamical confinement, and they are effects having a broad range of functionalization features in emerging nano and quantum technologies. And on the other hand, geometry of such system is most useful from the experimentalist point of view. In addition, a time-dependent box allows to have a tunable system with different regimes. This slide presents how a PT-symmetric system arise. For example, it can be using discrete optical materials with absorbing and reflecting properties, resonators with absorbing and reflecting walls, and using quantum materials like graphene, quantum Majorana wires, and etc. Let me briefly recall the problem of time-dependent box. The dynamics of particle in time-dependent box can be described in terms of this non-stationary Schrödinger equation, for which time-dependent boundary conditions are imposed. Using these special transforms for coordinate and wave function, we can reduce this Schrödinger equation into the form with static boundary conditions, and then it becomes non-stationary Schrödinger equation for harmonic oscillator whose frequency is time dependent. Boundary conditions of such equation are given in unit box. Also, let us briefly recall static boundary condition, static PT-symmetric quantum box. So, as I mentioned it before, a PT-symmetric system can be introduced by imposing proper boundary conditions. One of the example is that the Robin type boundary conditions, conditions that are presented in this slide. This solution of the wave equation can be written analytically using this simple form, and while energy values are the same with in the case of Hermitian counterpart, except we have here additional eigenvalue alpha square. So now let us proceed our main problem, quantum dynamics of particle confined in PT-symmetric box with moving wall. The time-dependent version of the boundary condition is presented in this slide. So in this case, it's shown that the norm is not conserved here. Now again, we use special transforms for coordinate and wave function. We reduce Schrödinger equation into the form with static boundary condition again. I would like to mention here that this transformation for wave function is different than in the case of with directly boundary condition. So then then one can get this Schrödinger equation with these boundary conditions. Of course, it's well known boundary condition, Neumann boundary conditions. So, and also here, if alpha is zero, you can see that the form of the equation will be the same in the case of Hermitian counterpart of this system. Okay. Not working. Um, so solution of Schrödinger equation above can be written in terms of complete set of eigenfunctions, unperturbed box eigenfunctions. So it's simply cosine imposed Neumann boundary condition. And so after so by substituting this psi into the equation and multiplying both sides phi star, and then integrating over space, we give us first a system of first order ordinary differential equations with respect to expansion coefficients. Of course, after using this orthonormal properties. Solving this system numerically, we can compute the wave function of the particle confined in PT-symmetric quantum box. And then having found the wave function, one can compute average time dependence of observable quantities for our system. For instance, average kinetic energy, average quantum force, and geometric phase, in other words, Berry phase, etc. The average kinetic energy describes acceleration or deceleration of the particle of the particle under the dynamical confinement. So it can be computed using this formula for our system, and also one can compute average quantum force acting to the particle by the moving wall. Can be computed using this formula. In our study, we considered 3 types of Walls motion: breathing box, expanding box, and contracting box. This slide presents results for breathing box. So average kinetic energy is plotted as a function of time at different values of oscillating amplitude and frequency and the parameter alpha. So for all cases, average kinetic energy fluctuates, and there is no monotonic growth or decay. There is no monotonic growth of decay as a function of time. So this is the specific property of PT-symmetric system. Pumping of the energy does not cause the monotonic growth as system undergoes to losses. And here the plots are presented as a function average force as a function of time at different values of oscillating amplitude, frequency, and parameter alpha again. So unlike the behavior of average kinetic energy, average force demonstrate certain quasi-periodicity in figure A and B, or even periodic in time, periodic in time can be observed in plot of the average force in C. Average energy and force are plotted as a function of time for quadratically expanding box at different values of acceleration of wall B. So unlike the case of Hermitian counterpart, where contracting size of the box cause growth of the energy in time. The figure A demonstrate growth of the energy. So this is unlike the case of its Hermitian part. So the PTC metric system undergoes to gains and losses. It provides it provides escape of the particle. And so completely opposite behavior can be seen in figure B, time dependence of average force, decays in time. This slide presents results for quadratically contracting box at different value of acceleration of the wall B. So here energy decreases while force increases. So physically it comes from the fact that the value of the average force depends on size of box. In both cases, the size of the box increases. The value of the average force is same in Hermitian and also PTC metric cases. Now this slide presents the comparison of time dependence of Cn of t squared and L of t for expanding box and contracting box. It explains that, of course, mathematically, it explains that the behavior of average kinetic energy and force above. So in the system evolving adiabatically, if the parameter changes adiabatically along closed curve in parametric space, the wave function of the system can acquire geometric phase in addition to the dynamical one. It is found by Michael Berry and after named him. So in our case, this parameter is very slowly changing wall, very slowly moving wall. So the geometric phase or Berry phase can be found using its definition as it presented here. For our case, it is computed analytically and it's complex. Finally, so let me briefly mention a sketch for experimental realization for our model, for our system. So it consists absorbing and active materials containing the empty void, the void, empty space or void between them. So the motion of the electromagnetic wave in empty space can be is described in terms of our equation with PT symmetric boundary condition, boundary conditions. Time dependence of this media can be provided in mechanical way. It means that this absorbing and active media can be moved by shifting in mechanical way. So let me summarize my talk. Dynamical confinement in a PT symmetric quantum system created by a quantum box with a moving wall is studied. The exact solution of the problem is obtained for different regime of the wall's motion, physically observing characteristics as average kinetic energy and average quantum force are computed as a function of time. Geometric phase is analytically calculated for a harmonically oscillating wall. I forgot to mention that this geometric phase is calculated for harmonically oscillating wall. Experimental realization of the model is discussed by proposing sketch based on the using PT symmetric gain and loss media. So I would like to thank to Professor Karsten Trank from Technical University Ilmenau in Germany. He's here. And Professor Miloslav Znoil, Nuclear Physics Institute, Czech Academy of Science in Czech Republic, and Professor Davron Matrasulov, Turin Polytechnic University in Tashkent in Uzbekistan. Thank you for your attention.
Can you return to the shrinking interval? Yeah. So you took a shrinking, but you didn't take it to the end. Because finally it contracts to a point. So the question is whether the energy at the point when it disappears go to zero and the force to infinity or not. The finite limits.
Yes, but energy goes to zero because
when the zero would be 10 because you didn't get so far in the
yes.
pictures.
Thank you for your question. So, so of course, in mathematically, if we draw this for more time, energy goes to zero because the means so energy cannot average kinetic energy cannot be negative. In physical point of view, if we more shrink this quantum box, the particle of the inside may escape from this quantum box. It means that in that case, there is no particle. It means there is no any probability inside the box. It means that there will not be any kind of energy. In that case, no, in that case, if we have a Dirichlet boundary condition, and energy will not be decreasing. In that case, energy will increase to infinity. Because in that case, particle cannot escape from this interval. It means that more shrinking the box, the energy increase into the
program and make the constant dependent on time.
I'm sorry?
If you take program condition And you make the parameter in the Robin time dependent. Okay. It's not fair.
You show us numerically that for periodic lengths of the interval, the energy remains bounded. Is it only numerical result or can it be analytically?
For oscillating wall.
Sorry.
No, so we have this this system of first order ordinary differential equations. So we can, as I know, we cannot solve this analytically because we have here the summation over with respect to m. So it means that we have many differential equations. We did numerically. We calculated numerically.
Okay, you are able to solve only numerically, but maybe you are able to obtain some qualitative estimates or something like that.
Maybe, but no, we didn't. We haven't done yet.
Okay, yeah, so.
Thank you for your question, by the way.
I don't know maybe it is name, but the question arises my thoughts. We speak about PTC and you have some equation, boundary condition, and arise is it something doing with operator responding to the problem, and because at the beginning I don't see, for example, the definition of symmetry or what we mean by symmetric, and then PTC. What is PTC?
Okay, let me.
To do with operators corresponding to that problem. Also, for example, you show here despite of existence of complex number in boundary condition. Yes, eigenvectors they are abnormal, so they behave like subadjoint case. I don't know. That's right.
Thank you for your question. So here, so we have the P means this is the P means parity transformation. For example, if we affect this wave function, it means that we have this condition. Of course, so T means we this operator T time reversal. This operator effect. What does it mean symmetric symmetry here? This condition. So in our case, we of course I'm sorry I didn't put here. So we proved this condition for our system when by imposing this boundary Robin type boundary condition. Even it's static already considered and proved. We proved that for time dependent Robin type boundary condition, we proved this system is PT symmetric.
Another question? Other questions or remarks? So then let us thank the speaker again.
Thank you.
And I think we proceed with the group picture. We did many pictures in the past. We continue with They cannot see, right? Yeah. Does it break also? No. Yeah. Wow, the stroke is not really so. The stroke reverse. The stroke. Yeah. But this you can eat now, right?
Yeah.
This is really.
I'm not sure that it's good.
Yeah. Oh, that's a big guy. And you need one.
I will come and eat it.
But I also get real thoughts.
No, you have to be
Yeah.
I'm just saying.
Maybe we find something.
Well, somehow the condition that the boss purely imaginary on that so I'm getting right. So we start the afternoon session, and the first speaker of today is the boss, first and one, and his title is Essential Spectral Operators. And when you have the presentation.
Yeah. Yeah, thank you, Pavel. I will speak about what you said. And it's a joint work with Jussi Berndt, Philipp Schmitz, and Gerald Teschel, and it is accepted quite recently in Journal of Differential Equations. This is maybe not so important. And what I want to present today is a little bit different topic from the things I usually present within SOMPOTI, but I was thinking, why not to do today a little bit more differential equations? And the emphasis in this talk is on the word indefinite. So this will be the main part of my talk. I will explain later what is meant with indefinite. And I would say with this paper, especially Jussi and me, we studied these problems since we are born. Yeah. So and this is somehow the end point of the story, I would say. Yeah. So it's based on many papers we published before. Okay, good. Maybe I take here also the opportunity to explain what is essential spectrum. I just do it by words. I hope most of you will know. Essential spectra is all points from the spectrum. Let's say I have an operator A. I take all complex numbers lambda. And if A minus lambda identity is not fretful, then lambda is in the essential spectrum of the operator. And there are many different characterizations of essential spectrum, and so on and so on. Okay. I try to. Oh, this is the other one, right? Honey. Okay. Now I have it. So this is a setting, and I start with, so I called it classical Sturm-Liouville, in the sense of this is an object which is very well studied. Sturm-Liouville expression with 3 coefficients, so full equipped with standard assumptions, locally summable, p larger than 0, and the weight, which pops up as 1 over r, is also positive. Yeah? This is a standard theory, very well studied, and our goal for today is to be a little bit more precise than on the slides. Point and essential spectrum for indefinite Sturm-Liouville problems, and a new result about essential spectrum for classical Sturm-Liouville. Okay, this is the program for today. So we associate with this expression, with the differential expression above, we associate as usual an operator. And here in the beginning, we are only interested in essential spectrum. So boundary conditions doesn't play a role. Yeah? It's just a finite dimensional change. So we take any boundary conditions, doesn't matter. Yeah? Of course, we have to take boundary conditions in such a way that we get the self-adjoint expression. Okay. I don't want to go too much into details with these boundary things. I want more present the results. Yeah? So let's say we have to this expression, we associate an operator A in such a way that it is defined on the so-called maximal domain. This is all functions from L2, absolutely continuous, such that P times F prime is absolutely continuous, and that the action that tau applied to F is again in L2. Actually, in the weighted L2 with the weight R, also this I drop a little bit in explanations. And then we have to add some boundary conditions depending where we are, finite interval, semi-axis, axis, whether we have limit point, limit circle, and so on and so on. No? And please read it in such a way that we say, okay, we take a self-adjoint operator on the semi-axis here, such that the operator, corresponding operator is self-adjoint. This is enough. Yeah. Okay. And now I come to the perturbation result. Of course, for perturbation, I need the second operator. The second operator is of same style, yeah? With tilde, and the coefficients have the same properties. And the tildes denote now the second differential expression. And the differential expression generates some self-adjoint operator, which I denote here with A tilde. Yeah? And now we want to compare the essential spectra of A and A tilde. Yeah? So, okay, here comes the theorem. We need one technical, let's say, technical assumption. This one here. So Q over R is bounded close to infinity. Actually, this looks innocent, but it isn't. It implies already that we have limit point case at infinity, and the essential spectrum is bounded from below. Yeah? But this is a situation we like. We want to work in this situation. And now comes the result. Sorry, some condition. And of course, I cannot compare two arbitrary self-adjoint operators, then I get no result. So I have to compare the coefficients. And we want to do it in this way, not compact or something like this, but in this way. So you see that it is somehow at infinity, these two different coefficients coincide approximatively. Yeah? This is true for R tilde, P tilde, and for Q we get the weight into this estimate. Yeah? So if we have this condition, then as the last line, then the essential spectra coincide. Okay, what is new here? Of course, they are in many. It's a classical topic, essential spectra of Sturm-Liouville operators. What is new? New is, of course, but this was what we needed. No, not this one. This new is that we also changed the weight. This is new. This was not done before. Yeah, so there are results for P tilde and Q tilde. When both operators have the same weight, such results exist in literature, but not when all three weights are changing. Okay, but this was, you will see later, this is exactly what we needed for our indefinite problem. So we had first to solve this problem. Okay, so this is this is the basis of what comes next. Now comes indefinite Sturm-Liouville. As I said, this is a classic case, and indefinite is when we have both sides. Yeah, clearly. Okay, and why should one consider this? I make the argument very sloppy. Yeah, no, I just indicate. One example is Fokker-Planck equation, which looks a little bit like this. And if you divide by R, you get, you make some kind of separation of variables. And then you have on the right-hand side, you have Sturm-Liouville equation, but this R in general is indefinite. Yeah? So there it makes sense. And then I want to mention, because Valery Samolenko had it in his lecture, in his summer lectures, Kamasa-Holm is of similar type. Yeah? In general, Kamasa-Holm, yeah, this is a longer story I don't want to explain, but at some stage, you end up with such kind of equation after again after separation of variables, and this W again is in general indefinite. Yeah, I don't spend too much time on this. So there is some reason to consider indefinite Sturm-Liouville. Okay. And PT symmetric operators also. This is a little bit cheating because the real PT symmetric operators looks different. But I realized that the techniques which you see in this theory for indefinite, because when it's indefinite, it is no longer self-adjoint problem, no longer Hilbert space self-adjoint problem. You have to deal the things in a different way, and then especially these techniques can often applied when you study PT symmetric operators. I mean, it's not the same, but they behave in some sense the same. Yeah? Well, sometimes the same. Okay, good. Yeah, I've found it convenient to collect all assumptions in here in the beginning. So I will always assume this. And you see A and B are a little bit cheating because B already implies A, okay? So we will always be on the, now we go to the real line. Before we have been to the semi-axis. We go to the real line and always assume B, boundedness, close to plus and minus infinity. And this implies already limit point. This is technical details. And then for simplicity, we assume that our indefinite weight is not arbitrary indefinite. Yeah? So it is, it is, let's say, bad in the sense, bad is always sign changes. It is bad on some finite interval, here AB, and it is good at minus infinity and good at plus infinity. Yeah? And just to make it simple, we assume that we are negative, close to minus infinity, positive, and so on. It looks like this. Yeah? We could have more sign changes, of course, in the interval AB. This is a very important assumption. And now we can look at this differential expression. Everything is the same like Hilbert space, but the weight R is no longer positive, it is indefinite. And our assumptions I did one slide before. Yeah? So we want what we want to do. Okay, we want to study the spectrum of this expression, yeah, of this Sturm-Liouville, indefinite Sturm-Liouville expression. And we start with the essential spectrum. Yeah? And then later we can, of course, we cannot describe the point spectrum. We can only give some qualitative properties, yeah, like it can accumulate to this. We have there and there no non-real spectrum, stuff like this. Yeah? Okay, and we start with the essential spectrum. And the idea is already here. This is this is also classical, yeah? Glassman decomposition. We decompose this expression according to these three intervals. Yeah, and I go back here. And the idea is somehow, yeah, because our weight is here at minus infinity, it is strictly negative. Here it is strictly positive, and in the middle, okay, no? Anything can happen. And now we decompose it into three objects, and this one is more or less. I will do it now, but I want to say it before. So this one is like self-adjoint and anti-Hilbert space. Yeah. The other one is it's pressed wrong. This is a standard, standard self-adjoint operator in a. You can associate. Yeah. Now 9. Associate a self-adjoint operator in a normal Hilbert space, and the guy in the middle is somehow chaotic. Yeah? but it is well studied. Yeah, we have, yeah, you did the right. It is on a regular interval. It has compact resolvent. It has only point spectrum, and so on and so on. Yeah? So this is well understood since 35 years. And when you speak about essential spectrum, Glassman decomposition means you add artificial boundary condition at A and B, let's say Dirichlet, and then you decompose the operator on the whole axis into these three small operators. Yeah? Then you changed, of course, the operator, but only by additional boundary conditions, which is finite dimensional perturbation, doesn't change the essential spectrum. Yeah? For later, for the study of eigenvalues, this is not so simple. Yeah? This could have an impact on eigenvalues, but essential spectrum doesn't care. Yeah? So this is what we will now do. Yeah? So we associate now many operators. Maybe I show you all. So we have one which is defined on the, this is this K, which is defined on the line, and it has no boundary conditions. Yeah? This is the operator. This is our indefinite Sturm-Liouville operator we want to investigate. And the other one are auxiliary, let's say. Yeah? And then what I said, we add artificial boundary conditions here, Dirichlet at A and B, and get three operators. Yeah. So as I said, here in this here for the first one from -infinity to A, the weight is negative. So we get you remember -infinity is in limit point case. So we get an ordinary Sturm-Liouville operator in an anti-Hilbert space. Okay. Yeah. And the middle guy is more difficult to control, but as I said, it is well known from literature. It's a Sturm-Liouville operator on a finite interval, and it has compact resolvent, and hence it has no essential spectrum. Yeah? So this is done, and well, the other one is from B to infinity is the ordinary Sturm-Liouville operator. Yeah? So I didn't write it down. This a little bit regret. Now we have already some kind of result. The essential spectrum of K is clearly the union of the essential spectrum of K minus infinity and K infinity. Done. Yeah? It's yeah, it's the proof is one line actually. It's a little bit annoying because you have to define the objects, but the proof itself is like nothing. Yeah. Okay, and now what is now comes? Now we can do perturbations. No? We can use the perturbation result from before in classical Hilbert space. Yeah. Because now we can perturb our expression, do the same for the perturbed one, and then, because in the middle term we have no essential spectrum, we can apply our previous result to K infinity and K minus infinity. Yeah? And get then a description of the spectrum of the perturbed operator. This is what we do now. So sorry, this I already said. Yeah, I was a little bit too quick. Sorry. So this is still what I said before. Yeah? The essential spectrum of our integrated Sturm-Liouville are only comes from the essential spectrum of these two operators at minus infinity and plus infinity, and the middle part doesn't play a role. Yeah, and now comes perturbation. So we have a second indefinite Sturm-Liouville expression. One has to say for these kinds of results, it's not existing in literature. Yeah? It was not studied so far. Yeah, because also of the indefiniteness, and yeah, which satisfy our hypothesis. We associate
again, corresponding indefinite Sturm Liouville operator. And I think I explained it now enough. Yeah, now we impose the conditions we had before, yeah, in the perturbation result for classical Hilbert spaces. And now, of course, we have to do it at plus and minus infinity because we will apply it separately to the two operators. And yeah, maybe I don't stress this because yeah, I don't comment this too much. And then we get that this under this assumption, the essential spectra of these two indefinite Sturm Liouville operators coincides. No? Okay. And again, here, because of Glassband decomposition, the main ingredient was just the corresponding result in Hilbert space. So this is the way where you transfer, let's say, knowledge or techniques from Hilbert space to this indefinite non-self-adjoint operators. Yeah? So let us, I have still 10 minutes, I hope. We can also discuss a little bit eigenvalues. One can also show, maybe I show you all of this here. Yeah, we make it like this. With completely different techniques. It's so-called locally definitizable operators. This was a special topic of my PhD advisor, so I could use it here again. So one can, let us start with the first point. So what we now do, this I have to say, we had the perturbation result. Now what we do is the following: we try to say as much as possible about eigenvalues of the indefinite Sturm Liouville operator. So we have no second perturbed operator. We study the original one, yeah, and try to say something about eigenvalues. And then the first result is that the non-real spectrum of our operator is discrete, multiplicity 1. This is easy because it's differential equation. And it is contained in a compact subset of C, but it's not so clear. Yeah? Okay, what else? We have, maybe I go back. So let us, the essential spectrum of K, we forget about, this was the theorem I showed you. The essential spectrum of K, I have not mentioned it. The essential spectrum of K was this one, right? This we showed before. But this was Hilbert space operator, and this one now also Hilbert space, self-adjoint operator in Hilbert space. So these two together is a subset of the real line. So our essential spectrum under the corresponding assumption is a subset of the real line. Yeah? So now what we have is that, so if you have on the essential spectrum is only on the real line, eigenvalues can only accumulate to essential spectrum. Yeah? So the only possible accumulation is points on the real line, and this we discuss now a little bit. Yeah, so we try to make it smaller. Not all of the essential spectrum. Little bit smaller sets. So and then next claim is that the non-real spectrum can only accumulate to points where the spectrum intersects, where the essential spectrum of K infinity and K minus infinity intersects. This is always to do with locally definitizable operators. They have some properties. Sometimes they are alike, in some spectral subspaces they are like Hilbert space operators, sometimes not. And these results you can use to prove things like this. And then they cannot accumulate to points which belongs to the boundary, to the real boundary of the intersection of these two essential spectra, which have the property P. And P, I try to describe it with that the spectra are allowed to touch but not allowed to mix. whatever this means. And this is here, this is here, the precise definition. So lambda has the property P, for example, if I have the following. This is the left-hand neighborhood of lambda, and this is the right-hand neighborhood of lambda. Yeah? And then it's assumed that the left-hand neighborhood is the resolvent set of the 1K operators, and this one, the right-hand operator, is in the resolvent set of the other operator. So yeah, so lambda is in the intersection of the essential spectra. So, but the picture is like this: essential spectrum might hit, but might not overlap. Yeah? And the same for accumulation of eigenvalues. It's also not possible because you have a full tiny interval in the resolvent of the corresponding operator. This looks super special, but it isn't. It's very natural. Yeah, it is. Yeah, it's not a generalization just because you can do it. It's a generalization because it makes sense in applications. Yeah? I have pictures. Okay, and when we have when this lambda has the property P, also we have no non-real accumulation to this lambda. Yeah. Yeah. And maybe I love this next result, but I make it. I have to. Yeah. This is the next topic. This is here's a very important. This is about accumulation in gaps. Yeah. And and also when you look carefully. You have a gap in the essential spectrum, yes, and you have the boundary points, and when these boundary points satisfy some conditions which are listed here, yeah, like lambda. The third one is like a lambda has property P and is not an inner point of the essential spectrum. Then you have accumulation, yeah, or yeah, if it's not satisfied, you don't have. Yeah, but I'm running out of time, but yeah, you see, this is also a possibility to transport the results on accumulation in gaps to this indefinite setting. Yeah, I listed here Kneser type results, Hoffe-Beketov, in the sense of periodic storm Liouville. Yeah, you can also do it for periodic storm Liouville. And this you then can use. You see, here for example, this one K minus, lambda blah blah blah, and eigenvalues of K minus infinity accumulate to lambda. Yeah, and this you can describe with Kneser, for example. Okay, pictures. So this is one of the standard Peschel-Teller. Yeah, this is Peschel-Teller, one of the standard examples from quantum mechanics. And the indefinite function is just sine over the real line, and then we have so I have to make it very short. Yeah? So one guy has a spectrum negative half-axis, the other one has half-axis. Yeah? Okay, where is the intersection of the of these two essential spectra? Well, at 0. Yeah, and but in 0 there's always a small interval which is the resolvent of the other operator. Yeah, in the resolvent set of the other operator. So to make it short. The intersection of these two is 0, and then just you have to check the definition. 0 has a property P, so we have no accumulation at 0. And there is, and this with other techniques, you can show that this guy is connected with the 30 above. Yeah. it has 30 non-real eigenvalues. This you have to make differently. And here is a picture, but this is numerically. No? This is not. And then very quick second example. This is Coulomb-like potential. And here's the story. Well, this is exactly the same. K infinity has negative half axis, K plus infinity positive half axis. The intersection is again 0, but because we have accumulation of eigenvalues, you don't have property P. Yeah? And then, well, this is a little bit cheating. No, this is a little bit cheating. We cannot prove it exactly. We suspect they don't have to accumulate. Yeah, it could be. At least our numerics shows this. Yeah. So okay, thank you.
Thank you. Just time for one short question. Yes.
Really, thank you. I enjoyed it. For audience, for those of us who don't study spectral theory, I will just mention one more definition. Essential spectrum. Everything in spectrum, with the exception of eigenvalues of finite multiplicity.
Yeah.
And then when you speak about the joint operator corresponding to a problem, you said that don't pay attention to boundary condition at A. And how you know that without that we can't do anything? Because joint extensions require that boundary condition at that finite point. Yes. It is also a question, but my question is, when you consider the composition, your problem, your operator, which is considered on ray A plus infinity, you replace it by orthogonal sum of three operators. Yes, but when you speak about spectral properties of previous operator, I think it doesn't completely coincide with orthogonal sum. Because in orthogonal sum you can give different boundary conditions and get different things. Yes,
you're totally right. I mean, I tried to squeeze all together. When it comes to essential spectrum, then boundary conditions doesn't matter as long as you get a self-adjoint object, and then you can play. Because it's a finite dimensional change. The resolvents, if you change a boundary condition, the difference of the resolvents is one-dimensional or two-dimensional. So they have this, and when the difference of resolvents is compact, you have the same essential spectra. So as long as you speak about essential, the first part of my talk, you can forget about boundary conditions. I mean, you need them to define, yeah, but you can play around. Of course, in the second part, when it comes to eigenvalues, what I showed here, then you cannot play around. Then you have to stick with the original operator. Yeah.
Stop. Same. Speaker. No. That's not the one. Yes. So next speaker is, I'm not the speaker. The speaker is the second one, Jan Pekka, and his title is here. So the floor is yours. Full screen, please. Can you make it full screen? Yeah. Okay, go.
Okay. So thank you for the introduction and the opportunity to speak here. And today I would like to talk about our joint article with Pavel Exner, considering the vertex coupling interpolation in quantum chain graphs. Okay, next slide, please. Okay, and I would also like to thank Professor Exner, as he did most of the heavy work regarding definitions in my talk. So I will go through this part very quickly. Please. Okay. So in 2015, Pavel Středa and Jan Kučera used the framework of quantum graphs to describe and explain the anomalous Hall effect. But in their article, they needed their system to break the time reversal symmetry somehow. And this was inserted somewhat artificially as a presumption. So in 2018, Pavel Exner and Miloš Tatar proposed the simple coupling which violates time reversal symmetry naturally. And in the same year with Ondřej Turek, they devised an interpolating coupling between this R coupling we have met in the morning session and the delta vertex condition. And all of this became much more interesting with the consideration of PT symmetry, as we have already heard in the morning. So without further ado, let's get into our setting. Every quantum graph has three essential components: set of vertices and edges, which define the graph topology, the differential operator, which gives evolutionary equations on the edges, and the vertex condition, which set boundary conditions on these equations. Starting with the topology, our quantum chain might look something like this. It is a periodic graph. Here we have in the dashed square highlighted the elementary cell, which repeats infinitely. It is defined by three length parameters. The disconnecting link L1. L2 is the length of this upper arc, and L3 is the length of this lower arc. Firstly, we will consider the general quantum chain in which all of these lengths are greater than 0, but later we will also comment on degenerate cases in which either L1 or L3 goes to 0. We also need to fix the scaling somehow, and in our case, it is beneficiary to consider the sum of L2 and L3 always equal to 2 pi. State space of our quantum graph are L2 functions on this graph. We will call their elements phi j. Then we define the differential operator, also naturally called Hamiltonian. Because we work with atomic units, it is only it only acts as a negative Laplacian with the domain of Sobolev space H2 on the whole graph. And finally, we must set some vertex condition, which most general form of this vertex condition can be expressed in this way. U is some unitary matrix, and both the function and its derivative are evaluated at a given vertex. Okay. This unitary matrix U belongs to the class of circulant matrices. We have already met them several times this morning, but also in the first lecture from Jürgen Prestin. And Pavel Exner already told us about the interpolation coupling. So the only new thing here is definition of the delta coupling and the R coupling in the terms of these circulant defining coefficients Cj. it's not difficult to express this interpolation coupling explicitly, but for us, the much more important thing are its eigenvalues, which we have written here. And for the future, I would like you to remember the only thing that if we choose gamma to be equal to 0, which is also the case of the Kirchhoff coupling, then this first eigenvalue, which we denote by j equals to 0, then this eigenvalue is independent of the interpolation parameter t. This will become relevant when I show you some pictures in the end. Because we work with a periodic graph, we can use Floquet decomposition and reduce our spectral analysis to the discrete spectrum of the fiber operator. And our final Hamiltonian can be formally expressed in this way. And with this Hamiltonian, we can associate some quadratic form. These first two lines, they are mostly technical definitions, which are not that important right now. But I would like to focus on one thing. We can pretty easily express this operator delta, and because of the presence of this term on the right side, we can see that the lower bound of this quadratic form escapes to infinity as the interpolation parameter t goes to 0, which will again become important when I show you some pictures. Okay, finally, we can start solving our problem. We look for the solutions in the form of like wave equations with some coefficients aj plus, aj minus, bj plus, and bj minus. Because we are working in periodic setting, we have some additional conditions these functions must satisfy, and these periodic conditions called Floquet conditions give us some relationships between coefficients a and b. And after some additional technical steps, we finally get to the system of equations whose solvability is equivalent to this determinant being equal to 0. D is a diagonal matrix which has eigenvalues of our unitary matrix U on the diagonal. F is matrix of discrete Fourier transformation. This comes from the diagonalization of circulant matrices. And these matrices M and N basically encode these Floquet conditions into our system of equations. When we express this determinant explicitly, we get spectral conditions in these forms. For a general chain in which all lengths are greater than 0, we get this polynomial in K of the 6th order with some coefficients P. For these degenerate cases, it simplifies slightly into a polynomial of 3rd order with coefficients Q and W. And as an illustration, and you definitely don't need to remember that, but I want to show these coefficients here. As you can see, they are very complicated, and they are generally functions of these length parameters L1, L2, L3, of the interpolation parameter, and of the strength constant gamma. Yes. But even at this moment, we can make some general remarks. For any value of interpolation parameter between 0 and 1, there are no flat bands in the spectrum of our Hamiltonian. Flat bands are infinitely degenerate eigenvalues, and we can also say that they are a solution of the solutions of this spectral condition independent on this quasi-momentum theta. And also for a these steps are have like technical character, but for a general chain or this chain with L3 equals to 0, we can define this new angle theta and rewrite the spectral condition or band or gap condition into these two inequalities. It basically means that we hide those terms p6 times k to the sixth power and so on into the vz, and the parts next to sine theta and cosine theta into vs and vc. Despite the name of this talk, we will spend most of the time with the delta coupling. Firstly, because to our knowledge, it wasn't discussed prior, apart from some very specific cases for a general quantum chain. And secondly, the spectral condition has much simpler structure for the delta couplings, so it will, from the educational perspective, it's much easier to understand how we got to the results which I will present. So for the delta coupling, the spectral conditions simplifies into this equation: Vc times cosine theta equals to Vz. This Vs term vanishes completely. And if we want to find these flat bands, these eigenvalues independent of parameter theta, it means that we want to find k's, values of k, for which this Vc vanishes. And I have written the Vc for the delta coupling here explicitly. So it means that we need to have k basically equal to some natural number. And if we choose k in this way, then we want to find conditions for which will the Vz also vanish. So we get to the fact that if L3 and consequently L2, because of our scaling fixation, is equal to P over Q times pi, where P and Q are natural numbers and coprimes, then K squared of this form is an eigenvalue for all possible P. If we are working with the gamma equals to 0, the Kirchhoff coupling, this statement is also valid for length L1. And if L3 is equal to P over Q times pi and Q is even, then there are these additional eigenvalues of this form. And finally, for general L1, or like for general L1 and gamma not equal to 0, there might be another flat bands stemming from solutions of these two equations. Yes. Think from solution of these equations. When we go to the high energy asymptotics, our spectral condition attains this form up to some big O k2 minus first error. And at the first glance, we can see that this spectral condition is independent of the strength parameter gamma. This can be easily understood from the fact that the delta condition is a potential energy type interaction. And for high energies of the system, this this condition becomes much less relevant. In the morning, we have also heard about this spectral characteristics, the probability of a random positive number belonging to the spectrum, and also how it is independent of the actual lengths of the graph as long as they are incommensurable. And for our quantum chain with delta coupling, it must be calculated numerically, as this condition cannot be simplified further. But if we do it, then we get to the probability which is equal approximately to 0.43. We can see how this incommensurability condition is vital, as for the fully symmetric case in which L1 equals L2 equals L3 and all of them equals to pi, this probability can be expressed analytically and is equal approximately to 0.78. Here, as an illustrative picture, we have the subset of the spectral volume, which is equal to these 0.43 if we calculate it numerically. When we consider the low energy behavior of this delta coupling, we do a Taylor expansion of this spectral condition, and up to some O to O, big OK error, we get this spectral condition. And the basic idea which we work with here now is that we take tangent of gamma half as an independent variable, complete the square with respect to it, and finally get to these conditions. Basically, if tangent gamma half is in those mentioned intervals, then the lowest positive band extends to the energy k squared equals to 0. And these intervals depend on the length ratios of our graph. And we can also see that all of these intervals are negative. And because tangent of gamma or tangent of gamma half is an odd function, then we can clearly see that the spectrum threshold, positive spectrum threshold, is positive for gamma greater than 0. If we are to consider the negative spectrum, we simply take our spectral condition and replace k by I times kappa, where kappa is greater than 0. And here we consider the, let's say, strong theorem from Baradwaran, Exner, and Tatar from year 2022, which basically says that if our elementary cell contains n vertices with some couplings described by unitary matrices, then the negative spectrum of our Hamiltonian has at most some over nj plus negative bands, where nj plus are eigenvalues of the corresponding unitary matrices in the upper complex plane. So from there, we can say that the negative spectrum for the delta coupling is non-empty only if the coupling is attractive, which means the gamma is less than 0. And in that case, it consists at most of 2 negative bands. And because the Taylor expansion of the spectral condition is up to some error is exactly the same for both the positive and negative spectral condition, we can say that the first positive and highest negative band are either both separated from k equals to 0, or they extend to this point simultaneously. Here we consider the first degenerate case where L1 equals to 0. For it, we have additional additional flat band at this value of momentum k, where now L3 has the same form of pi over q times pi, but here now p can be also even. In the high energy regime, of course, up to some error, our spectral condition gets this form. And from there, it can be simply seen that if those lengths L2 and L3 are equal, which means this mirror symmetric chain, then our chain is fully conducting and our probability is equal to 1. But if those lengths are non-equal, but still together they get to 2 pi, this probability is equal to 1/2. Low energy behavior is basically done by the same procedure, and we get this condition for which is the positive spectrum. The positive spectrum extends to the energy k squared equals to 0, but it can be also done by the former limit from those interval I have shown you earlier. Okay. And we have at most one negative band for negative gamma. For L3 equals 0, we have additional flat bands at these values of L1, and this P and Q must satisfy this condition. In the high energy regime, we get this condition, and for it we know that for any value of L1, our probability is equal to 1/2. For low energies, we get this condition, and again we have at most one negative band for negative gamma. Finally, for our interpolation coupling, for high energies, we get this spectral condition, like in the highest term of this spectral condition are clearly negative, so the gap condition is valid. So bands can only form around points of this structure for which this part vanishes completely. And again, by doing Taylor expansions, we can say that asymptotically the widths of these bands behave constant for some m if the lengths are common measurable, but otherwise they behave as OM2 minus first. And together from this we can say that our probability is equals to 0 for any value of interpolation parameter between 0 and 1 included. And our chain is basically non-conducting for high energies. For low energies, we don't get any reasonable insight as the condition obtained by the Taylor expansion is too complicated. But again, we can say that the negative spectrum is connected only, is connected to 0 only if the same is true for the positive one. For attractive coupling, we have at most 4 negative spectral bands. For gamma greater than 0, there are at most 2 of them. And in the limit t goes to 0, the maximum number decreases correspondingly. And here we have some illustrations. This spectral picture was done for Kirchhoff coupling, so gamma is equal to 0. We can see some structures similar to Dirac cones. We think that these stem from the fact that the first eigenvalue I have mentioned at the start of the talk is independent of the interpolation parameter. And here we can see those 2 bands which escape to infinity as t goes to 0. But aside from that, the spectrum is empty. This other picture was done for attractive coupling. Again, the specific value of gamma is not important, but it is negative. And here we can see again those bands escaping to minus infinity, but also those new bands stemming from the attractive coupling. Finally, these degenerate cases for general T. So flat bands are still absent, and the behavior around k squared equals to 0 is still unchanged. But in the high energy regime, we get these same spectral conditions as we got in the case of the delta coupling. So to repeat, for L1 equals to 0, our probability is equal to 1 only if L3 and L2 are equal to pi. Otherwise, this probability is equal to 1/2. And for the degenerate chain with L3 equals to 0, our probability is always equal to 1/2. This concludes my talk, so thank you for your attention. That's perfect.
They said Mia Bordaeva, and the title is Bordaeva problem fraction loaded equation, the big side.
Thank you very much. My talk about the boundary value problems for a fractional loaded equation of mixed type. I would like to note about the loaded equation and mixed type equation. And of course, in the last of the section, it's about new results with PhD students, height bias. How we know the mixed type equation? It's very important in the classical partial differential equations. At the moment, this kind of equations can include all possible combination. It's maybe possible will be parabola hyperbolic or parabola elliptic or parabola hyperbola elliptic and others. This kind of equation arises especially in parabola hyperbolic types in gasoid dynamics, electromagnetic fields, and magnetic hydrodynamics and others. The first of this kind of mixed type equation, it's introduced by Trikami. And after this equation in the one of the part of the domain is elliptic, in the other side equation will be in the hyperbolic types. What about if equation not only with one type change of lines? It's possible will be maybe two type of lines with changing type. What about this kind of equation? This kind of equations arises after 2000 years and investigated in the works of Karimov, Kabada, Islamov, Salakhadinov, and others. And the other side, our equation is loaded. This kind of equation, it's very important in some of the applying problem of mathematical biology, for example, in the problem of dynamical population, and some of the problem of optimal control problems, and some of the investigation problems, for example, in the linearization of nonlinear equation, investigation of inverse problem arises this kind of equation. This kind of equation, loaded partial differential equation and loaded integral differential equation, it's very important if it's possible to write in the sum of the two operators. The first part is the partial differential part, and the The second part of the equation is a loaded part, which is the containing maybe with integral operator or integral differential and others. For example, in these equations is a phenomenon in complex evolutionary system with memory essential depending on the prehistory of the system. And this kind of systems is described by the following loaded integral differential equations. The first one, elliptic types with the Laplace operator, and the next one is the parabolic. The next and another example is this kind of hyperbolic type equation. It's found in the theory of wave propagation in dispersive environment, where uxt is the density. Or the next equation is a partial differential equation of the first order. It's describing modeling of the movement of the vehicles on the highway, where phi x t y is the density of the car in the point of x. We can show a lot of examples, this kind of loaded equations, and it's very important. One of the equation is the McKendrick and von Forster equation. Well describes the closed population with the boundary conditions, next boundary conditions, and initial conditions. This problem is described closed population. If in the case from population in each time t removed the singular ages E1, E2, and E3, equation can be written in the next form. The next equation is the loaded, such as the last of the part of this equation is the loaded part. A is the age, T is the time, UAT, it's density after T times individ in the age of A. In the other side, this kind of equations, it's a loaded equation, it's very important that this kind of equation equivalently reduced to new kind of boundary value problem as called as non-local problem for classical partial differential equations. We can to see in the one of the examples, this one equation of the first equation in the hyperbolic type with the loaded operator. D is the integral differential operator loaded. If we are investigating for equation one, some of the problem of Cauchy-Goursat or Darboux, classical problems, I can to reduce our equation one to the classical partial differential equation, but with non-local problems equivalently reduce the conditions 3 and 4 in this form. This one. For the classical partial differential equation, we can to reduce the problem with the non-local conditions. This one, W and W prime, it's depend on the Z on the another the point of AB, another characteristics. It's this kind of conditions is where W, it's this one. It's depend on the Z. And Z must satisfy the classical partial differential equation of the third order. That's why we can to see the loaded equation as loaded equation for the local boundary value problems or a classical partial differential equation with non-local conditions. Next. Formulation of the boundary value problems with 1 and 2 type of change lines. Let omega 1 be the rectangle with the vertex, this one. And omega 2 and omega 3 let be the characteristic triangles. this one. Omega 1 is this rectangle, and omega 2 and omega 3 is characteristics triangle, which is bounded with characteristics wave equations. In the domain omega 1 and omega 2, we investigate the following equation. Да. It's just one. Не, вначале хотела. Sorry. So equation 1. We consider the following loaded integral differential equation 1. In the domain omega 1, omega 2, and omega 3. When omega 1 and x and y greater than 0, our equation will be in the parabolic type, as this one is equal to 0, and our equation is a parabolic. When in the domains the omega 2 and omega 3, our equations will be in the hyperbolic, because in this second part of this one is equal to 0, and our equation will be in the hyperbolic types with the telegraph operator. We are investigating this following loaded integral differential equation, where Ak is dependent on the loaded members with connecting with integral differential operator D. And this D is the integral differential operator in the sense of Riemann-Liouville. And we suppose that alpha E and beta E is less than 0. And if alpha E and beta E is equal to 0, our operator will be in this form. The next. If we are investigating only with one characteristic, non-characteristic or characteristic type changing lines problems, we can to prove the existence and uniqueness formulating problems. The first we would like, we can to investigate auxiliary problems, problem with non-characteristic line of changing type. In this case, our problem will be formulated in this form. Find the solution to equation 1 in omega, possessing the following properties. Uxy is continuous in the omega, closed omega, and has continuous derivatives in the first order. And continuously glued, satisfies the gluing condition, this one, in the line of when y divided from 0 to 1, and satisfies the following boundary conditions. And the next, we can to investigate the problem with characteristic line of changing type. We investigate two problems. The first with omega 1 and omega 2, the second omega 1 with omega 3. And the next step, we must investigate this kind of problems is in general domains omega 1 and omega 2 and omega 3. And the next problem is investigate our results, some of the results, and this auxiliary problem is this kind of find the solution to equation 1 in omega prime, and it satisfies this gluing conditions, and also with the boundary condition, this one. In 5, 6, and also in the 3. And the next step in these two problems, we can to prove existent and uniqueness formulating problems with regarding of some of the conditions of the given function phi2, psi2, and for the given coefficients, with some of the conditions, we can to prove existent and uniqueness formulating problems. The next steps, we will consider the equation in the all of the domain omega-1, omega-2, and omega-3. In this domain, we investigate the following problem. Find the solution to equation 1 in omega and omega prime with the following properties. Uxy is continuous in the all of the domain omega and omega prime. It's all of the domain omega-1, omega-2, and omega-3, and has continuous derivatives of the first order and satisfies the following gluing conditions. And satisfies the boundary conditions 7, 8, and 9. It's these conditions is given in the lines of B0, the function of U, and our next condition is given in C0 and B, the function of U, and also given in the characteristic AC. We can to define the regular solution in all of the domain omega-1, omega-2, and omega-3, the following formulating problems. And of course, here is our gluing conditions of the continuous gluing conditions must satisfy in the line of A0, the first order derivatives and the function of U and derivatives, and also AB must satisfy the gluing conditions, the function of U and derivatives of the first order. And our main result, if the function of A and the function of BE is satisfies the following conditions, and alpha E, beta E less than 0, and given function is satisfies the condition of 10 and 11, and there exists a unique solution to the problem of 3. How we can to prove the following theorems? The first, when studying the problem 3 in omega-2 and omega-3, our equation 1 can be written in this form, 12 and the next one. And this two equation in omega-2 and omega-3, our equation as hyperbolic type, where Xi is x minus y, its characteristics. And the first, we investigate problem of Cauchy for this kind of equation. This equation is a hyperbolic type, but with the loaded operator D. We introduce the following notation. U x equal to plus and minus 0 in y, its latitude will be in tau 1. This is tau 2. This is nu, the first derivative is nu 1 and nu 2. We denote this designation in these lines of A0 from the side of omega-2. Its latitude will be tau 1 nu 1, and from the omega-1, it's in the side of the next omega-3. Its latitude will be tau 2 and nu 2. As our conditions is uxy is continuous in all of the domain, that's why in this this x equal to plus 0 and minus 0, it's equal, as our gluing condition is continuous. The same in the first derivatives, also continuous gluing conditions. Here is a tau 1, nu 1, and tau 2 and nu 2 is unknown function. The first, we investigate the Cauchy problem for equation is 12. With the conditions of this one and 2. And we can write our solution of the Cauchy problem in this form. Where is the E is E0 and E1 is a modified Bessel function. It depends on the coefficient lambda. If it's a lambda is greater than 0, it's modified Bessel function. If less than 0, it's Bessel function. With regarding of our Riemann-Hadamard function for this kind of equation as telegraph operator in the main part, we can to write the solution of the Cauchy problem in this form. But here is a tau 1, and here is also tau 1, and here nu 1 and tau 1. It's unknown function yet. We satisfied for this solution. The next. This solution, the first boundary condition where is given in the omega 2. And if I satisfy the first one conditions, I can to receive this integral differential relation for the function of tau 1, nu 1, and the first, as given the first condition, psi1. We receive this integral differential relation in the line of type of changing lines from the hyperbolic side. The same in the next hyperbolic side, we can to receive the second integral differential relation in this form. From the omega 3 in the line of AB, we can to receive the second integral differential relation using the second boundary conditions. It's depend tau 2, nu 2, and also psi1. Psi1 is given functions. Here is a tau 2 and nu 2, it's unknown function. From hyperbolic part, omega 2 and omega 3, we receive two integral differential relations in the line of type of changing. What about the parabolic side? In parabolic side, we must to receive two integral differential relations. The first in the line of AA0, the second the first integral differential from the omega 1, we must to receive two integral differential relation from the omega 1 in AA0 and from the omega 1 to AB. We received at the moment two integral differential relation from the omega 2 in the line of AA0 and from omega 3 in the line of AB. The next from the to receive integral differential relation from the parabolic side. Similarly of the work in 2, it's we can to see in the next in the reference. Here is analogously in the work of 2. Our equation as with the parameter of lambda, we know it's very easy to write in the form without the lambda. Without loss of generality, we can to find this kind of changing of variables, and we can to write our equation equivalently in this form. And this equation in the parabolic type with the parabolic operator in the main part, this is the loaded part. For this equation, we will investigate the first initial boundary value problems for this equation. This is the loaded integral differential equation, parabolic types. If we investigate the first boundary initial problem for the in the rectangle, we can to write our solution via the function of tau 1 and tau 2. It's unknown function, and we satisfied the conditions, the next condition in the conditions of the Cauchy, difference for the x and passing to the limit x to plus 0, where arrives the next integral differential relation for the function of nu 1, tau 2, tau 1, and others given function. This is unknown also. From the parabolic side, we arise the integral differential relation from the parabolic side in the line of AA0. This is the third integral differential relation from the parabolic side. In the next, from the parabolic side, we must receive second integral differential relation. For this, it's with regarding of formulating problems, the first and second conditions, we can to passing to the limit from the equation 1. And if we are passing to the limit plus 0, we obtain the second integral differential relation from the parabolic side. It's directly to the integral differential relation equation, integral differential equation of the first. Related with the function of tau2, nu2, and this one. This is the second, this is the last one, first integral differential relation. And that we obtained 1, 2, 3, 4 integral differential relation in the lines of AB and AA0. And this integral differential relation for the function of tau1, tau2, nu1, nu3. To define these three unknown functions, we receive three integral differential relations and system of integral differential relations. And if we can to prove the existence and uniqueness, formulating system of integral differential relations, we can to prove the problem of three. Mm-hmm. Excluding the function of nu1 and nu2 from the first integral differential relation 21, 23, and 24, and taking into account these conditions. And when alpha e beta e less than 0, we can to receive the integral differential relation, this one, 22, and also 23. Where K2 and fx is a known function, it's depend on the given functions. The next, if we excluding the function of tau2, we can to receive the next integral equations with regarding of property of integral differential operator. We can to receive integral equation type of Volterra 24. Where K1 is a kernel with a weak singularity, f is this function is depend on the given function. With regarding of condition of the theorems and with the conditions of the function of C1 and C2, we can to prove existent uniqueness this integral equation 24, and we can to define the function of tau1. If we can to find tau1, we can to define tau2 and also nu1 and nu2 to construct our general solution in the domain of the omega1 and omega2 and omega3. If we know tau1 and tau2 from the hyperbolic side in the domain omega2, we can to reconstruct our solution with the solution of Cauchy problem, as we know tau1 and nu1. Or we can to construct with Cauchy-Gursa solution of the Cauchy-Gursa problems. The same in omega3. In omega2, we can to determine our solution with first boundary initial conditions with the function of green function. We can to reconstruct our general solution in the domain omega1 also. And same as our integral equation is type of Volterra, we can to prove existence and also its uniqueness also. And same as we can to prove existence and uniqueness and formulating problem of problem 3 also. And I would like to note that this formulating problem is in our gluing conditions is continuous. As we can to investigate this boundary value problems with not only continuous conditions, with some of the general discontinuous conditions of some of the integral discontinuous conditions. Also, we can to investigate the formulating problems. This kind of general discontinuous gluing conditions for the with one line of changing types equation were investigated in the problem in the results in the 3, and also and with with integral discontinuous gluing conditions, but with one type changing lines investigated in the problem of 2. But in our case, we proved these boundary value problems with continuous gluing conditions. And this was in our last results in the journal, Applied Mathematical Journals. At the moment is a preprint. Thank you very much.
Question, so if you couple your equations always on line segments, would it be possible to consider more general domains, say with a smooth boundary between them?
Yes, it's maybe at the moment it's maybe a little difficult. Its beginning works as a parabolic hyperbolic type equation. This kind of equation it's helped me, of course, in this domain. Its beginning we investigated in characteristic domains. It's helped me to investigate the formulating problems. Maybe it's a little difficult. Maybe next we must think about this kind of general, not only characteristics, triangles, maybe general domains also. But at the moment, I don't know.
The question, higher dimensions. If the surface is not a curve but a surface or hypersurface.
It's we have only one. I have only one result in the parabolic hyperbolic type equation in the 3-dimensional domains. But n-dimensional domains, we have some of the results with loaded integral differential operator. But for a hyperbolic type equation, at the moment, we are investigate this kind of problems in n-dimensional domains. It's new. Thank you. Thank you very much.
You involve your singularity in your integral differential equations if your derivative usually and randomly derivative. How do you involve your singularity?
I would like to note that in this case, our integral differential operator in this form, and alpha is e less than 0. In this case, our integral equation kernel and right hand side will be only big singularity. If alpha e less than 0, if alpha e greater than 0, here is very problem. In this case, we are not investigated yet. Alpha e less than 0, here is the singularity is less than 1. That's why we can't prove existent uniqueness.
Great, 26 minutes. Speaker Aslanov department.
Thank you, Professor. I would like to present the next problem. As you see, a force of the differential equation. Coefficients are, it is not ordinary differential equation. Coefficients are operators. They are not real or convex functions. And you see some boundary conditions. In fact, here at the beginning, okay, firstly giving some which kind problems are covered by that was. For example, A, that operator coefficient, it might be some, for example, Laplace operator, and H with some kind, such kind space. So it is it plays a role of good modeling for partial differential equations, for boundary value problems for partial differential equations. Okay, what was down? I just want to escape all that part. Why? Because you see that boundary condition, if I will turn to the beginning, boundary condition involve a lambda parameter too. Here it's a special case, particular case when some Nevalina function of lambda parameter is contained in boundary condition. Here it is contained linearly in for force of the differential equation. Okay. What we did here, we firstly, if you wish to connect to that problem, some self-adjoint operator, sorry, you can't do it remaining in a previous space, in L2 space. You have to go to exit space. You have to go to exit space. And in exit space, it is a good late foundation theory for that, how it might be made self-adjoint. Okay, in that, just look, direct sum space, bigger space, H sub 1 space, which is, it is not the product here comes, it must be, it is imperfection, typo. It should be the direct sum, orthogonal sum, okay? Yeah, so to previous one, to L2, we add 2 copies of H. Only here you can do it self-adjoint and so on. Which kind questions studied? Firstly, given definition of minimal operator corresponding, covering such problems, maximal operator, you see it is domain by that theorem, in theorem 2.1, given definition of maximal operator. Also given given conditions for self-adjointness and by in terms of boundary conditions, conditions 2.7. Also given conditions for discreteness of spectrum, it's theorem 2.3, and studied. Here comes proof. Given condition, studied asymptotics. Considered it is particular case, namely the case when y0 equals boundary conditions 3,2. I mean, here studied asymptotics of eigenvalues. Okay, these are asymptotics of eigenvalues. I will turn to it. Also, given conditions when its resolvent might be from sigma p. Also, give. Slow down. I'm afraid that nobody can follow. Okay. Maybe it is because of I want to skip it. Yeah, 1 moment. Okay. Okay, you can, the last theorem gives also a condition when spectrum will be any interval of real axis. So I just want to tell you that you see here we give condition for discreteness of spectrum for the operator giving with the same differential expression. Also for having a continuous spectrum, all that possible. It depends on boundary conditions in that case. When you have operator coefficient A. So in terms of A, you can give also definition of self-adjoint extensions having continuous spectrum, even with previously known spectrum. So if you wish that spectrum to fill in some interval, you can do it. It all depends on boundary condition. So in it, I think it differs from when Professor Trank, when he said that for scalar Sturm-Liouville operator, it was not the case. Okay. All that it was why I passed that so fast, because I presented it in Austria, in Vienna, where I presented also Professor Exner. That part was given there. I want to concentrate attention at the next moment. At what? Look, about operator A, we have some conditions on it, providing discreteness of the spectrum. We have that is self-adjoint and it is inverse from compact. It is inverse is compact. It provides discrete spectrum. Okay. Then its eigenvectors, which are denoted here phi k, they form basis. They form basis in space H. H is abstract Hilbert space. So any vector from domain of previous problem with operator coefficient might be expanded in terms of that basis like that you see that series. And when doing it, instead of previously considered problem with operator coefficient, you come to system of 5154, which is system of scalar fourth order ordinary differential equations. Just eigenvalue problem just for that one. So in place of operator coefficient, say you you get gamma k's. Gamma k's here are eigen values of operator A. So A's are when passing to such expansions, they are replaced by gamma k's. What is the main statement here? Characteristic determinant. For example, if you have some nth order differential equation, say on some finite interval, it has n fundamental set of solution consists of n vectors. Yes, general solution you can write by using that fundamental set of solution. Then writing that general solution into boundary conditions, you'll get some equation for determining eigenvalues. It's mainly doing like that. Yes. Okay. And if you speak about eigenvectors or eigenproblem, you are interested in non-zero solution of equation and boundary conditions. Yes. And for that non-zero solution to exist, it is you have when writing boundary conditions, you have some system of linear equations, algebraic equations in C1, C2, Cn, which are constants, arbitrary constants. Okay, and to have that such a non-zero solution, determinant of that should be zero. Yes, and that determinant, as you know, it is said to be characteristic determinant. Yes. Okay. Now, characteristic. It appears that between characteristic determinant of equation, for example, we are speak about that particular equation, between this characteristic determinant and between its norm, so between norming constants, between this characteristic determinant and norming constants exists, not that was, I want to go back. No, I'm going after. Exists some relation, what namely, that characteristic determinant derivatives, it appears that it gives norm of eigenvectors. Such interesting fact. And I prove it here. Why I decide to do it? Maybe I will say you if I can manage to speak about proof of that one. Okay. Yes. Solution of equation 5152 5, 1, 5, 2. So equation 5, 1 and boundary conditions 5, 2 is given by means, where it is? It is given by means of sorry. Okay, gamma k, you see gamma k in terms of hyperbolic sine and hyperbolic and sine, some of the functions. So solution of equation satisfying conditions that at 0 it is value 0, second derivative at 0 equals 0, it is that one. And if you wish to find eigen values, you have to substitute that solution into second conditions, next conditions with lambda parameter. With lambda parameter. I want to go to equation. No, I'm doing something wrong. Okay, okay. You have to write that solutions that you see into 5, 3 and 5, 4. Yes, and also if you wish to define self-adjoint operator, you have to do it in that. Okay, in that space lambda is as you see, which is direct sum of L201 and copies of C, 2 copies of C. You can do it there only. So you should construct, you should consider not only that solution about which I said, sum of hyperbolic sine and sine, you also must construct such a vector, U2, U1, U2, but like that. It should be 3-component vector. Okay, when what happens? Okay. Yes, it was. I'm going back. Okay, when doing that, you get that equations 5.5, 5.6. If you find so the common roots of that equations, they define eigenvalues. They define eigenvalues of that problem. If you find C1 from condition omega 1 z equals 0 and substitute into omega 2 z, you will get characteristic equation. By using that, I form that I compose that function 5.9 fkz. I compose that function. In fact, that function again I'm repeating since omega 2 z vanished there, it differs from omega 1 z only by you see it only by factor yk1z4. So by functions, by solution of equation. So it is not completely a characteristic determinant. It differs from characteristic determinant, which is in fact omega 1 z. It differs by factor gamma k, yk, sorry, by factor yk. It differs from it by factor yk. And it appears that function's derivative give for zkj cubed their roots of characteristic equation. And what stands next to it, norms of eigenvectors, orthogonal eigenvectors. So its derivative makes norm of eigenvector. It gives norm of eigenvector. Here come the next justification of that fact. What is down here? Here, consider it problem firstly with lambda, then with lambda kj, both of them real, then subtracting from multiplying the first one by gamma k, the second one by gamma k, lambda minus gamma k, and subtracting the first equation from the second, you get that one, that relation, which is on right side of which, after factorization z4 minus zkj in fourth degree, after factorization that common factor, what remains there? It's norm in fact, square of the norm of eigenvector in that direct sum space. But what remains? What about expressions that we have on the left side? Here, I applied twice just integration by part, and again back. After doing that, I get I group everything in such form. Just look 5.14 that look at expression within brackets, within square brackets, and. What appears? It appears that if you remember, on the left-hand side, on the right-hand side, we have norm multiplied by z4, z in fourth degree minus zkj in fourth degree. On the right, I get that you see that expression for n. Of 5.14. And it appears that if you will divide both sides of that equation by z minus zkj and go to the limit when z goes to zkj, and if that conjugates of gamma k's third derivative at zkj fourth degree, if that conjugates will be real, we will get derivative of that function, of that ratio, gamma k third derivative over gamma k, I mean z ratios. As if we have z ratio minus z ratio at z ratio at zkj in fourth degree. And if that conjugate pairs also appears to be real, it will be derivative of that function at point zkj, yes? If you will pass to the limit when that but what was the problem at the beginning? When for gamma yk, we have concrete value. We know that it is C1 hyperbolic sign plus C2 just sign. But that functions, one more moment, roots in previous case that I skipped, roots of characteristic equation that becomes to be real, that the characteristic equation have real root, as well as it has imaginary root, as well as it has roots of form, complex roots of form, y plus iy, where real and imaginary parts the same. It is proved. But how to justify that their conjugates will be also real? If they are imaginary, it is easy. If they are real, it is also easy. But what about roots of kind y plus minus y, because such roots also exist. And certain idea here was come from the fact that gamma k's in fact they satisfy the boundary conditions. Gamma k's derivative dividing gamma k equals lambda kj, and lambda kj's are eigenvalues of self-adjoint operator, so they are real. So that ratio it doesn't depend how that functions numerator and denominator. In fact, that ratio always real, always real. And also that, let me again back. Okay, let me state that really it's derivative of that ratio. Derivative of that ratio. What I get on the right side, derivative of that ratio. And after simplification, I get 5.15. But how it is related to characteristic determinant, question might arise. If you remember at the beginning, I said that characteristic determinant, it differs from function fkz is composed by characteristic determinant. It differs from it only by one factor, gamma k. And that's why I take it and derive and get the same things that we have earlier. So anyhow, it was justified. Really, characteristic determinant derivatives makes norm of eigenvector up to multiplicative constant for zkj cube. Zkj's are roots of characteristic determinant also. Why it was so important? It was important for me for evaluating so-called regularized traces. Okay. I'm not good at that. Running. I think I give that. Okay, regularized trace. Regularized trace, you know, it was formerly done, Galfand-Levitan's famous work when they consider it to Sturm-Liouville problem, differing from each other by boundary conditions. You know that eigenvalues have such asymptotics. You see, lambda n equals n square plus, okay. N squared plus c plus big O 1 over n squared. So they can't form a converging series, but you can regularize it in some sense. How to regularize? Even that asymptotic says you have to regularize, subtract from it n squared. If c vanishes without losing generality, or subtract also c, you get sum of big O 1 over n squared, which will be a convergent series. And they give value of that sum in terms of potential Q0 plus Q pi dividing 4, like that. Such problems were also treated for Sturm-Liouville operator equations, even high order differential operator equations, when considered two operators differing from each other by some bounded operator Qt, and it was proved that in some sense when subtracting their eigenvalues, you will get again converging series. But what's the problem here when you study equations with operator coefficient? About asymptotics of eigenvalues, you don't know everything, as it was in previous case, in scalar case, when they see that. For example, where you see that the lambda n equals 1 squared plus c plus O big O 1 over n squared. You know, just it is a principal part of that asymptotic. So you have in some sense justify that what you mean under regularization and so on. It's one direction of studies. Okay, but okay, but in that work. Which was published in 1984 in Daklat Akademi Naukaser, and it was proved that such regularization was given, and you see that sum come to, you see, that sum lambda n minus nu n is expressed by means of qx, that's operator again, depending on x. Phi i's, they are in fact eigenvectors of operator A. So you get something expansion of that scalar function. Scalar function, I mean qx phi I times phi I. You have, it is expansion in terms of cosine, and Fourier expansion in terms of cosine kx is like that, and that's why it is easily proved that you can get such value, it's that function value at 0 plus such function value at pi. It is a Fourier expansion along cosine k pace. But how to be when you change a bit boundary condition? You have not Dirichlet boundary condition. For example, you have some the first is y0, 0, second bits modified, y prime p minus lambda y equals 0. Here, everything changed because now your eigenvectors appears to be okay, your eigenvectors are psi kj's, which are sine xjk t phi j, and you see that xjk's here are not integers; they are roots of some transcendental equation. And you have sum that you have is not expansion along any known series or known functions, as it was in that case. So you have to find value of such a series, of such a double series, how to be. And here, firstly, we applied Cauchy residue theorem. Cauchy residue theorem. So select some function of complex variable whose poles will give us terms of that series. And the problem in fact is reduced to selection of that function, composition of the function, how to find that function. I just directly take, as you see, okay, partial sum. Here you see partial sum. For it, how to select function. Okay, I just put rudely characteristic determinant in the denominator, in numerator right, in numerator to z questions to z t. You see that it. Go back. Okay, a numerator dictated by numerator of series, and really it worked. I was able to find to evaluate value of that sum. It was possible, and afterwards it was applied repeatedly many times. Each time I'm taking concrete characteristic function, write it into a denominator, and get what I mean. What it signals? Signal comes from here that between characteristic determinants and norming constants should be some relationship. But why I don't do it in that last work? Because in that last work, series that we get, or norms of eigenvectors, just look at that eigenvectors 4.1. If you wish to evaluate the norms, it will be in 2-page, about along 2 page, you have to write this norm, if you wish to find this norm. So you can't see here some clues, some connections between things. That's why you have to give some general way, if it exists. General way, it really exists. Okay, that problem takes us to justification of that theorem. I am repeating, in which I said that it was proved that derivative of characteristic determinant gives us norms of eigenvectors. It was down here. Okay, have I time? I don't know. 1 minute. Then I think I can say too much during that 1 minute. Okay. Everything good. Thank you.
Okay, since the next speaker also will be replaced by Ariel Savira. Ariel Savira. Then we just merge and go next.
The presentation is there. Yes. You can pass this here. Okay. As announced, the next speaker is Sabirov, is speaking about their function.
Title of my talk, Dirac particles on periodic quantum graphs. I will talk about some briefly. Outline is given here. At first, I will talk about networks. After this, network science, graph and the topology, the equation on graphs, relates quantum mechanics, periodic graph, and Dirac equation on periodic graphs. Then spectra of the Dirac particles, probability to be in the spectrum. Networks everywhere. Networks appear almost every part of nature, of life, and life from atomic and nanoscale physics and to condensate matter of ethics from small bacteria to human organism, from information system to social life and economy and financial networks appear in even at astronomical systems. Networks are used for model broad variety of complex systems from macromolecules to WWW, social, economic, political, and ecological system. Mathematical terms in networks are represented by graphs. Graphs is characterized by its topology, connected rule for graph bonds. Graph topology of the graph, that is the way the vertices and bonds are connected, is given in terms of the W times V times V, connectivity matrix CIG, where connect CIG is given here. If I and G vertices are connected, then CIG and CGI is equal to 1, and otherwise it's equal to 0. Here given some types of graphs. The first is star graph with one vertices, the ring graph, very regular graph, complete graph, tree graph, etc. Wave function psi is a big component vector. The first component is on the one bond, and second is second, etc. Relativistic quantum mechanics, when the particle or wave moves with a velocity comparable to the light speed, its motion is described in terms of relativistic wave equation, which has Dirac and Kleingarten and Bogolov-Djun equations. Dirac equations given here. This is Dirac equation where our H bar and C is equal to 1, and here this Dirac equation, and where where m is mass and v is column potential. And here given some another two component Dirac equation. This is two component Dirac equation. This is two component Dirac equation. Alpha is equal to this one and beta is equal to this one. And here these boundary conditions for boundary conditions we can boundary conditions we can obtain from this relation, this Hermitian form, where this scalar product is our Dirac operator, and here from equating to zero this skew Hermitian, and from boundary conditions we can define this equal to zero. And in these papers we can see for the Kazakhstan the first Kazakhstan are derived boundary conditions for the Schrödinger equation, for the Schrödinger operator, and Bolter-Harrison are derived for the Dirac operators on the metric graphs. Here given some considered for the Schrödinger operator with the Schrödinger equation with the quasi-periodical boundary conditions. And for the periodic graphs, we consider the following periodic graphs. If you see here, this unit cell, different of these periodic graphs are given in this slide with unit cells. Here, on this unit cell, we consider the following Dirac equation. This is two-component Dirac equation. And with these boundary conditions, these are our boundary conditions, and this quasi-periodic boundary condition. From these boundary conditions, we can derive that skew Hermitian is equal to zero. And here, general solution of these of the Dirac equation is given by this one. This of a general solution of the Dirac equation, and from the general equation, using these relations, we can find the following relations for our constants, and from here we can find secular equation where S is scattering matrix. This is scattering matrices. And band spectra is important characteristic of the periodic quantum structure is its band spectrum, which is eigenenergy spectrum as a function of the system parameter. It's characterized most of the electronic properties, including electronic conductance. Band spectra of the Dirac particle of the periodic column graph lengths are fixed, where these are lengths fixed, and the first is for the beta is equal to 0.2, and for the beta equal to 2.5, this is equal to this one. Another here given probability. If you see here, we can find probability from this picture we can find. And here for this unit cell, if you see here, difference between of them are topology of the graph. Topology, if topology of graph is different, then our probability is different. Therefore, here we can see from this picture. Thank you for your attentions.
Other parallel graphs other than the comp shape?
If you see here, just a moment, please, just a moment. Here. For this, for the first periodic graphs and the third, for the third, band structure is similar. But other graphs, topology are different. Therefore, band spectrum is a different. Picture of band spectrum are different because this depends on topology of the graph.
Dispersion curves. Your pictures of dispersion curves.
Just a moment.
Here,
This one. This one.
So it's that in the left picture, all the gaps are open, while in the right one, some gaps are closed, which and it depends just on the value of the parameter. That's
This parameter from this parameter beta.
Different. So depending on the parameter, you can close and open the gaps.
Yeah, because if you see here, we have lengths are different. Our unit cell, if you see here, here, just a moment. This is our unit cell. This is our unit cell. L1 is this one. L2 is this one. Therefore, dependence between all of them.
That some gaps are closed if L2 is larger.
Larger, yeah.
Is that the case?
L1 is more larger, I think. Just a moment. L1 is more larger.
Yeah.
L1 is more larger, not L2.
No, I said the closing gaps. The second picture. The second picture, and that corresponds to L1, which is larger.
Yeah. L1 is larger.
So it's the general property. It's a turning point at L equal 1.
We didn't consider.
Somebody needing one for everybody. Yeah. Yeah. Yeah.